email them to you?
What's that?
We email them to you?
Yeah. Email, put hard copies with hand calculations in my mailbox, and then electronic files, email them directly. Thank you, Chris. All right. Went through, talked about, just a quick recap on variance, right? Talking about variance is just a metric of variability. Same thing, standardization, just a different metric of variability. Sum of squares, just another metric of variability. So they're all telling us kind of the same thing. We're just kind of changing them around to look at things a little bit different. Again, when we're talking about our standard deviation, that's typically what we're reporting as a descriptive statistic, just because that's an easier thing to interpret. Roughly interpreting standard deviation a couple of different ways as the expected distance of any randomly selected score from the mean, the distance between any two randomly selected scores in a distribution. We think about standard deviation in terms of error or deviation, average deviation from the mean value. Again, it's not exactly an average because of that sample correction that we make here, right? Dividing our sum of squares by the sample minus 1, but conceptually thinking about this in terms of how we understand standard deviation. Okay. Questions about variance? Okay, so I'm going to switch over and start talking about covariance. Okay, covariance is going to be just a rough metric of the extent to which two variables vary with one another. Okay, formula for, or the definitional formula for covariance. Again, don't ignore these. Take a look at these formula and make sure you kind of understand what's going on. It'll help you conceptually. What we're doing is we're taking the sum of the deviation score for a given x, multiply this by the deviation score for a given y variable, and dividing that again over n minus 1. Okay? So if we think about what's going on or why covariance ends up giving us a rough measure of association. Let's say we've got depression scores on the x-axis and PTSD scores on the y-axis, right? These are two things that are obviously correlated with one another. Not perfectly, but in general there's an association, right? If I know something about your depression score, I probably can guess something about your PTSD score here, right? So if we take a look in this situation, think about how this graph relates to our covariance formula here. If I have large x values paired with large y values, the sum of those products, the deviation scores are going to be large and positive, right? So if I've got a big x value, right, Chris, where's my, let's say I have like this one right here, what's my deviation score going to be for this case in terms of x? If this is the mean and here's my observed score.
Oh, it's going to be positive, like 15?
Yeah, it's going to be big and positive, right? And again, if I go through and multiply this, or actually let's take this one, right? So we've got a big deviation, positive deviation from the mean. What's my deviation and my y value here going to be?
Maybe positive like 20-ish?
Yeah, big and big, right? So I've got a big number multiplied by a big number, right? So if I pair large x values and large y values, these are going to be values that exceed or sort of much higher than the mean value of the sample. I'm going to have the sum of my product, my deviation scores, are going to be large and positive. Same thing if I have small x scores and small y scores, right? So this score down here, we'll keep with you, Chris, here, on a roll, buddy. So what's the deviations, the x deviation score for this case going to be?
Like -22.
Yeah, negative, right? And what's the y deviation score going to be?
Like -40.
Right. And if I take two deviation scores that are negative and multiply them together, what do I get?
Positive.
A positive, right? So if I have large x values paired with large y values, with small x values paired with small y values, what we're going to get is a large positive covariance, right? On the other hand, if I have large x values paired with small y values, right, what I'm going to get is some of the cross product, or some of the deviation scores, or the product of the deviation scores is going to be large and negative, right? So let's say I've got a score here, right? Nick, where's this score going to be in terms of my x deviation? Large and positive?
Y, negative.
Large and negative, right? So here's my X value, right? And here's my mean, here's my score, hypothetical score up here, there's no score up here, but let's say there was, right? My deviation score is going to be negative because my X is far below the mean, right? If I pair that with a large Y value, or a small Y value, something that ends up way down here, right? Or no, a large Y value. So I've got a negative X and a large Y, right? So a high deviation from here. Same thing down here. If I have a high X value paired with a low Y value, some of the cross products are going to be negative, but again, so my covariance is still going to be pretty large. On the other hand, if my X scores are unrelated to my Y scores, right? Sometimes my X scores are going to be paired with a large Y score, sometimes with a small Y score. Some of the products are going to be negative, some of them are going to be positive. We sum all those up, what we're going to get is something that's a covariance that's very close to zero. Yeah?
Quick question. So what can I get from covariance that I cannot get from correlation?
Hold on to that real quick. Okay, so the question was, what can I get from covariance that I can't get from correlation? We'll see that in just a moment, but that's a good question. That's kind of where we're getting, right? So covariance, think about covariance as very similar to a variance estimate, right? If I just say, oh, I have a covariance of 1,000, is that a big value or a small value? I don't know, depends on whatever scale we're using, right? So covariance, like variance, is a general metric of association, but not one that's super interpretable just right off the bat. Right? So if we go through, same thing with variance, we have a definitional formula here. If we look at it, we can kind of see what's going on. This is a computational formula because this can be sort of hard to go through and calculate. If you want to do something, you go through and calculate. These two things are equivalent, but if we're going to get covariance. Okay? So people get a general idea of what's going on with covariance and how we calculate this, why this all works. Okay. So, again, covariance is going to be a joint function of the standard deviation of our x's and our y's. Okay. But not a lot of, Ignacio, as he was talking about, not a lot of interpretive value. I can't just look at it and say, oh, this is a large association or a smaller association. But if we go through and we take that covariance estimate and we divide it by the product of the standard deviation of x and standard deviation of y, what it does is it standardizes that. It brings it down into something that starts to make sense, okay? And what we get when we take our covariance and we divide it by the product of the standard deviation of x and standard deviation of y, this gives us our Pearson product moment correlation. This gives us our correlation that we know and love, right? Something that is bounded by -1 and 1, that gives us something that we can interpret very easily in terms of the strength of association, okay? So just like variance is important computationally for ANOVAs and things along those lines, same thing with covariance. It becomes important in sort of the behind the scenes calculation and stuff like that. What we want to do is generally take that covariance, translate it into a correlation if we want to look at bivariate association between things. Okay? So this is the formula for our Pearson correlation here. Covariance divided by the product of the standard deviation of x, standard deviation of y. One thing we need to think about though, and we've talked about this previously with different types of statistics, our R coefficient, our Pearson R, is not an unbiased estimate of population parameter rho for small n's, okay? So if I have a small sample, I have a sample of, say, 30 people, 20 people, something like that. My Pearson correlation is not an unbiased estimate of the association between those two variables, okay? Is it going to be too big or too small? What do you think, tomorrow? Too big, right? Because if I've got a set of data, right, and I've only got a couple of values, what's that correlation going to look like? Strong and positive, right? It's going to go right through here, right? But if I go through and I add in like a bigger sample, what I'm likely to find is that in general, maybe that's the real association. when I actually collect a decent amount of scores, right? With a small number of scores, things can start, it starts to inflate that Pearson correlation, right? And so what we can have, remember this is similar to when we were talking about our hedges G, we talked about an unbiased G, a downward correction for small samples. What we can do is we can calculate an adjusted R, which is going to be our equal to the square root of 1 minus the squared value of our coefficient times the number of people in the sample minus 1 over n minus 2. Run through that. What that's going to do is it's going to be downward shrink that a little bit. Okay. So what we can see is as this as that our sample size starts to increase and increase and increase and increase, it's going to be dividing this correction by a larger and larger and larger number. It's going to make that correction get smaller and smaller and smaller and smaller, right? So at very large samples, my R adjusted is going to be very, very close to my estimated coefficient, but at small samples, it's going to provide a bigger downward correction. Yeah.
When we say small sample size, when are we deciding to adjust the value?
Yeah, this starts to be hard, right? And it's kind of a judgment call, right? You often won't see people report an adjusted R squared, or excuse me, an adjusted R. Probably they should, right? I mean, if we've got samples of size 20, 30, I'd probably be calculating it and just seeing what it looks like, right? Looking at the discrepancies with anything, right? If I calculate sort of my adjusted R squared and my R, and sort of this is say 0.4 and this is 0.38, probably not a big deal, right? But if I'm working with like a sample of 15 or something like that, right? Say CJ is doing an experimental study and you got small cells and things along those lines, and you have concerns that maybe in a sample of 15, 20, correlation is important conceptually, but sort of not wanting to overstate the magnitude, right? Might think about an adjusted value there. Questions on this? All right. So, hypotheses test for our R coefficient. Our hypotheses here are null hypotheses. So this is rho, this sort of P-looking Greek letter here. Rho is equal to 0. Rho is just the notation for your population coefficient. So here we're saying the correlation in the population is equal to 0. We would also say X and Y are linearly independent. Again, when I'm asking you to provide me the null and alternate hypotheses in problem sets, make sure that you're working in exactly what the measures are. Just don't tell me the association in the population is 0, because I'll grab that too for not. You can tell me exactly what association we're talking about, what the population is, so on and forth, so forth. Our alternate hypothesis here is just that the population coefficient is some non-zero value, okay? Or X and Y hold some linear relation. Okay. In terms of what we use as our actual statistical test, luckily for us, simple enough. The sampling distribution of R, given a population value of 0, is going to follow a t-distribution with n minus 2 degrees of freedom. Okay, so when we're talking about the sampling distribution, what are we talking about in terms of sampling distribution? Okay, so let's say I've got some variable x and some variable y that are completely uncorrelated, no association, right? And I go through and I sample x and y with sample 100, okay? Alicia, if I go through and I sample, so I got a sample of 100 people. In population, the actual population value of this association is 0. I go through and I sample 100 people and run the correlation between x and y. What's my value of R going to be?
0.
Is it going to be 0? It's going to be exactly 0 in my sample, my random sample of 100. Is it going to be exactly 0? Is it going to be something big? let's say it's 0.08, okay? And then Nick, I go through and I run another sample of 100. What's my value now?
Somewhere around there.
And let's say negative 0.10, right? And I do this again, 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 right? We know that even if the population value is actually, it's true 0 in the population, right? But for every sample I get, it's never going to be exactly 0. It's going to be something, right? And if I go through and I plot over an infinite number of replications of sample size 100, what I'm going to get is I'm going to get a distribution, right? This is my sampling distribution, right? And so sometimes, CJ, am I never, ever in my lifetime ever in samples of 100, never going to get a large value?
You will.
I will, sometimes, just not very often, right? Sometimes I might get something, you know, negative 0.30, sometimes 0.30, right? So I'm gonna, on average, or just over the course of doing this over and over and over, on occasion, I'm gonna get some weird stuff that should go up on the tips. But in general, I'm not. I'm probably gonna get stuff that falls right around here, right? And so when we're thinking about the sampling distribution of our Pearson correlation, what we know is this sampling distribution here is going to follow a t-distribution, right? We know t-distributions, we love t-distributions, worked with them a lot last semester, right? And so what we can do then is, because we know that the sampling distribution of R, as we calculate it, follows a t-distribution with n minus 2 degrees of freedom, then we know what the sampling distribution is, and now we can go through and test it, right? So again, remember our hypotheses tests are saying, assuming that the null hypothesis, or assuming that the null hypothesis is true, assuming that the population value is indeed 0, what's the likelihood of me finding a correlation of X value? Is it likely? Is it not likely? So on and so forth. Okay, all this stuff kind of coming back, right? So what we can do then, because we know it's, because R has a known sampling distribution, we can run an inference test with that and get actual, very specific probability values for our coefficient. And so what we can do then is we can take, because this follows a known distribution, we can calculate a t-statistic based on our Pearson correlation. Take our coefficient times the square root of n minus 2 over the top of the square root of 1 minus the squared value of our Pearson correlation. That's going to give us a t-statistic. Then all we need to do is use that t-statistic to calculate p-value, just like we always do with n minus 2 degrees of freedom, and we're good to go. Okay? So Siley, with sample size of 100, what's our t-distribution we're going to test against? So how many degrees of freedom? If I have a sample of 100?
You have
90?
No, 1.
Or minus 2?
Minus 2, yeah. So 98.
98, right? So we look at it, to compare our t-test against a t-distribution with 98 degrees of freedom. Remember that t is just a family of curves. Every individual curve, depending on the degree of freedom, has a slightly different shape, right? And so we just go ahead and test that against here. One thing I'll say, people sometimes make this mistake, in calculating your t-test, this always needs to be your actual observed coefficient, not R-adjusted. If you want to calculate R-adjusted as a better population estimate, do that, but don't put R-adjusted into your t-statistic here. Okay? So, questions on how we go through and test the significance of our Pearson coefficient. Okay, pretty easy, straightforward. What I would do is I just use our online p-value calculator. You just calculate your t-value, drop that in, degrees of freedom, you're good to go. Okay. Questions? All right. Nice thing about R is it's a correlate, or it's a measure of the association between our two variables. It's also maybe one of our most basic measures of effect size. Okay. This is nice. If you calculate an R, you're essentially calculating an effect size, giving us an estimate of the magnitude of an association within the population, right? Standard conventional benchmarks for interpreting the magnitude of R small, R equals 0.1, medium 0.3, large equals 0.5. Again, these are very, very rough estimates. This is Cohen's benchmarks. No, people do it anyway. You shouldn't, right? So thinking about things medium to, so if I get a correlation of 0.8, I'm going to call that small. I'm so small to medium effect, right? Or if I get something that's point, you're just being careful in terms of your interpretations, just like we did with T's, right? Also, this not being the end-all, be-all in terms of importance, right? We may, on occasion, find associations that are quite small, but still very, very meaningful and important, right? But this just kind of gives us a metric to gauge strength of association. Straightforward transformations back and forth between D and R. Anybody work at this point within labs or another class working with meta-analyses types of things? You'll often see, right, effect sizes reported as R's, right? In general, I've got different studies using different methodologies and different analyses. It's nice within the context of meta-analyses to bring everything back to a common metric that we can kind of generally gauge sizes on. R is generally what people will use in terms of magnitude of an effect. So if I have a Pearson correlation, I can take that Pearson correlation, multiply it by 2, take that, divide it by the square root of 1 minus the square of my R. That's going to give me a rough estimate of D, right? Also, I can take D, divide D by the square root of D squared plus 4, gives me an R. I can start to move back and forth between these metrics to be able to report the thing that makes the most sense to me. So remember, again, benchmark small, medium, and large is based on Cohen's framework, 0.2, 0.5, 0.8, right? And so what this allows us to do is go back and forth between things. Okay? Another thing we can do in terms of R, we can take R and we can square R. We can take that Pearson correlation, that bivariate correlation, and we can square it. What this is going to do is it's going to give us the proportion of variability in our outcome that's roughly attributable to variability in X. Okay? It's not the proportion of variability in Y attributable to variability in X kind of sounds like there's a causal relationship. There's not. It's just sort of saying if I know, sort of it's common shared variance, right? And so if I have a correlation of 0.5, and now see when I square 0.5, what does that give me? What's that?
A lot correlation.
Yeah, so, but if I take 0.25 and square it, what do I get?
0.25.
0.25, right? And so what I would say is that about 25% of the variability in X is shared with variability in Y, so giving us overlap here, right? And this is a nice way of reporting sort of level of overlap between two variables in the bivariate case, okay? So different options in terms of calculating effect sizes with our Pearson correlation. The Pearson correlation on itself is a nice measure of effect. I would probably don't screw with it. For some reason, if you wanted to change it over to a D, you could, right? If someone's reported to say, let's say I'm looking at my thesis, right? I'm trying to do a power analysis, and I pull up a study that Chris has done where he ran a t-test, but he didn't report a D. He reported it as an R for some reason. I'm not sure why he did that, but he just did it. But I really want to know, have that as a D so I can sort of use it, sort of think about that. I can take that R coefficient and move it over to a Pearson coefficient, right? Or let's say you reported a D and I want an R, I can move back and forth with that, right? Also, I can take that, square it, that gives me a proportion of variability. That's nice, right? So just knowing the different ways of looking at things, it's all the same information, but we can move back and forth between this. Questions here? All right, so let's talk about assumptions of our test. So if we want to take our coefficient R that we've calculated and use that as an estimate of population parameter, this test is, and our tests, our inference test is based on the assumption that my variable X and variable Y have been sampled from a bivariate normal distribution. Okay, so this gets a little bit tricky. We're all sort of familiar with our normal distribution, right? Talked about on a univariate case, sort of what that looks like. When we're talking about our Pearson correlation, we've got two variables, right? And what we need to do now is we need to now assume something about the distributions of both our X and our Y variables, okay? So in thinking about this, throw up sort of this, everybody up in the air, okay? This is your x coordinate, your y coordinate, okay? So we're assuming this is x, we're assuming normal distribution here, or y, normal distribution here, right? But as soon as we get into sort of bivariate case, we need to get into two-dimensional space. So throw that finger out like this, right angles to one another, and then do this, okay? So now what we've got is we've got distribution here coming up, and so what we got is a three-dimensional distribution that looks something like this grid right here, okay? So when we're thinking about this in three-dimensional space, right, what we're assuming, based on our correlation, is a conditional distribution. So we're assuming, let's start here, okay? Marginal distribution of x and y. Marginal distribution of x and y, this is what we all sort of think about and know about and sort of are comfortable with. We're saying the distribution of x is normal and the distribution of y is normal, okay? That's our marginal distribution, okay? But we also need to be concerned with conditional distribution of y. Conditional distribution of y says that the distribution of x for any y is going to be normal. So if I take this bivariate normal distribution and I go through and I slice it at any value of y, okay? What I'm saying, if we go through and slice this, is I'm saying that for any value of y that I go through and slice this on, I'm going to get a normal distribution. If I'm looking at it, I'm going to get a normal distribution of x, right? So if I had a very large data set and I said, I'm only going to look at the distribution of x for those individuals who score a -1 on y, I would see a normal distribution, right? And if I said, okay, I'm going to go through and take all people who scored a 2 on y and look at the distribution for all people who scored 2, x is going to set up a normal distribution, okay? This is going to be my conditional distribution of x given y. Same thing, distribution of y values for any x are going to be normal, right? So if I go through and slice this the other way, if I say, all right, for all people who scored 0 on x, what's the distribution of y? I would still see y has a normal distribution. If I go through and I say, for all individuals who score -2, what's the distribution of y? It's still going to be normal, right? And so what we want is to be able to go through in a bivariate normal distribution. We'll say the distribution of x is normal, distribution of y is normal, right? But this conditional distribution is saying, if we just restrict our set to any given value of x, y is still going to be normal. If we restrict it to any given value of y, distribution of x is still going to be normal, okay? So we'll see here, I got an asterisk here, for a conditional distribution of y given x, this is the only thing that's assumed in regression, right? So for correlation, we assume conditional normality in the conditional distribution of x given y and the conditional distribution of y given x. Both of those are important. When we move into a regression format, technically all we're assuming is that the distribution of y given x is going to be normal. And we'll talk about sort of why that is when we get into regression stuff. Okay. So, someone tell me what the shape of a bivariate normal distribution is going to be under the null hypothesis. People can think in three-dimensional space. Yeah, Chris.
So, from what I understand, what you cannot see in this graphic is that if you were to pivot it to face us, you would also see a normal distribution here. And then you would essentially have something like, if you were to have it on the board, something like jutting out at you.
Yep.
It would look like a nose, essentially.
Okay, yeah, so this one, if we rotated it, yep, that, you're exactly right. It would kind of look kind of thin and coming at us, right? And so, does this bivariate normal distribution suggest a correlation between x and y?
No. It does not, because they're independently.
Well, again, so you're right, because it's going to, if we were to rotate that, it would kind of look like a nose coming at us, right? Suggesting that things are kind of all lined up in one direction, right? So this actually would, if we do have a correlation between x and y, this is what the bivariate normal distribution is going to look like.
Okay.
What if the null hypothesis is true? If there really is no association between x and y, what's this distribution going to look like? What's that?
Flat.
Not flat.
anything else?
What's that?
I mean, wouldn't have that shape.
Wouldn't have this shape. Think about an anthill, right? Something that just sort of goes out the same sort of distance in all directions, right? Something that is still normal, no matter what way you look at it, but if we rotate it around, it would look the same in all directions, right?
Kind of look like this, right?
No,
Is it
because that's
linear on X?
that's still gonna indicate, so what we would see is, like literally, if you took sand and poured it from a bucket on the ground, it would just kind of go out in all directions. That's what if a null hypothesis is true, that's what that bivariate normal distribution would look like. So again, x, y sort of sitting up, it would just be completely in all directions, right? There's no association, there's no sort of, that distribution isn't moving in any direction. Here, what we're seeing is that so we're seeing sort of things kind of lining up all in the same direction right here. Under the null distribution, everything's going to be sort of kind of flattened out, right? So I can't rotate that in any way and see things sort of moving one way or the other. It's just going to be sort of all. If I were to take that distribution,
It goes backward in space and forward.
yeah,
in
yeah. So
space
we
and
would
out
see
in space.
sort of the same thing going out there, right? So if we take that normal distribution and just rotate it 360, that's essentially what
It's like a pizza.
no correlation would look like. A pizza that's loaded with toppings that comes to a peak at the top.
Like a cinder cone volcano.
What's that?
Like a calzone.
A cinder cone volcano, which is
Yeah,
like
yeah, yeah.
a cylindrical volcano.
That's right. right.
Like that?
It looked like a volcano. Yeah, yeah.
A funnel.
A funnel. Yeah. Right. So
I think we got it now.
anything we got, right? Okay.
I guess
Yeah.
I'm not picturing it, because I'm imagining if you move away from, like in the x-axis, if you move to 1 on an anthill, that y value will decrease with x. So the bigger x you have, the smaller, I mean, the bigger x you have, the bigger y you have.
Yeah.
And the smaller x you have, the smaller y you have.
Mhm.
So that's an x-y correlation, right?
Well, but it's going to be the same way, sort of in 360 degrees, no matter where you go. So basically, it's basically like a cloud, a scatter that's sort of, no matter what way you move in y, x, you get sort of change in y all over the place. No matter what way you move in y, you get equivalent change in x. It's an even distribution across the whole thing. So in sort of 3 dimensions, that bivariate normal distribution just kind of looks like an anthill, sort of goes, as opposed to something like this, where we've got kind of like a ridge. This is indicative of a correlation in bivariate normal space versus instead of having kind of a narrow thing, sort of everything going, it would sort of all fall out.
Would it look like this?
What's that?
Would it look like this?
No,
No.
Yeah, kind of.
it would be flatter.
Well,
It would be like a little bit flatter.
yeah,
Like a
yeah,
pizza,
so-
no?
Ish. So yeah, ish, maybe something like that, right? So this is not central for you understanding or sort of being able to execute correlations at all. But what I want you to be able to do is kind of thinking about conceptually what's happening in this bivariate space and sort of what things are going to be looking like in terms of your underlying assumptions. Okay. So again, why this is important is understanding sort of kind of geometrically, graphically, what a conditional distribution is going to be, because this is sometimes hard for people to kind of understand. Okay. Yeah.
There is no implication of any meaningfully sequence of events, right?
No. Yeah, this is all cross-sectional, so no,
Yeah.
there's no order.
It happens simultaneously.
Yep. Questions? Okay, cool. So, getting correlations in SPSS, pretty easy. You can analyze, correlate bivariates, so we go down through them. So it gives you your Pearson correlation, significance value, the number of people in your sample. Easy peasy. In SATA, simple too. Your command is PW core, variables that the 2 variables you want to, or whatever, how many variables you want in your matrix. If you add this sig command on the end, Alicia, that will give you your statistical significance there. So pretty easy, straightforward stuff. Okay. All right. So that's a quick overview of assumptions and correlations. People comfortable with this? Any questions about what we're talking about in terms of our correlations? Okay. So what we can do now is we can go through and take these coefficients and we can start to play around with these a little bit and sort of run some tests that might be relevant to project-specific types of things. One of the things we can do is we can go through and compare independent coefficients. Okay? So in this scenario, what we're doing is, let's say, Ignacio, what are you doing research on?
Today?
Yeah, I don't know, any day. It's a hypothetical.
Well, the relationship between the pleasure I have between my pizza and this new burger parlor is in the theory. I don't remember it.
Okay, so let's say correlation between pizzas sold and hamburgers sold, right? And you just want to know, sort of, are these two things related to one another, right? So you go through and you look at the correlation between pizzas sold and hamburgers sold, right? But you do that in the States, right? Maybe what you're interested in is, does that hold? Do I see the same thing in other areas, right? So maybe I want to go through and look at pizzas, the correlation between pizzas sold and hamburgers sold in Germany, right? So it's still the same metric. It's still the same thing, right? I'm just wanting to see, the US population is different than the German population. There might be differences across these two. Pizza burger correlation might be different here in the States than it is in Germany, right? And so maybe from a marketing standpoint, sort of investment standpoint, this is something we're interested in, right? What we can do is we can go through and test, if I get the correlation between pizza and burgers in the US, pizza and burgers in Germany, I can go through and test to see if there's differences, if I'm getting evidence of differences in the strength of those correlations across different populations, okay? And so this is what I'm doing here. So my null hypothesis here is the difference in population coefficients is 0, or row 1 is equal to row 2. My alternate hypothesis is the difference in population coefficients is some non-zero value, and one's bigger than the other, right? So row 1 is not equal to row 2, right? And so we've got two Pearson correlations, right? And we want to test the two of them. Problem is that the distribution of R1 minus R2 is complicated, okay? So we know that the distribution of Pearson correlation by itself follows a t-distribution, right? But if I take the sampling distribution of correlation 1 minus correlation 2 and subtract those two, it no longer follows a t-distribution. It follows a different distribution. It follows a paranormal distribution that we don't understand or know what it's going to be on. We can't predict it, right? And so what we need to do is we need to do something. So we can't just, if I don't know what the sampling distribution of a statistic is, I can't run a hypothesis test on it, right? And so the characteristics of the sampling distribution of R1 minus R2, we can't predict it. So we can't do a direct test on this, okay? People sort of following sort of what's going on here. So what we do is, if we can go through, and what Mr. Fisher figured out is, if we go through and we transform that R coefficient into a Z, what we can do is then we can start to go through and actually make this test. So we use Fisher's R to Z transform. Anybody ever heard of Fisher's R to Z transform before? Okay. Basically, we're just taking that Pearson coefficient and we're transforming it into, we'll call it R prime. Okay. So R prime is going to be 0.5 times the natural log of 1, or times the natural log of the absolute value of 1 plus your coefficient over 1 minus your coefficient. Okay. And if I do that, what we know is that the distribution of R prime, this is approximately normal with around rho prime, with our standard error being 1 over the square root of n minus 3. Okay, standard error is really easy to calculate. There's no complicated formula. So the issue is R by itself follows a t-distribution. That's nice, so we can test whether or not R is 0, right? But what we can also do is we can take R and we can transform it using Fisher's R to Z into R prime. And now, instead of following a t-distribution, it follows a z-distribution, right? With standard error 1 over n minus 3. So if we do this, what we can do is we can just take that R prime, that transform. Now what we can do is we can go through and actually calculate a difference, right? And so what we do, if we want to say, let's say I want to see whether or not the correlation in Germany, or the correlation between pizza and burgers are different in the US than in Germany. What I do is I take the correlation coefficients, translate that using Fisher's R to Z into R prime. And then what I can do is I can calculate a test statistic. I can take R prime for the US minus R prime for Germany over square root of 1 over however many people we sampled from the US, 1 over n minus, or how many people we sampled from Germany minus 3, gives us a Z statistic. And our Z statistic, we can just calculate, sort of use that, calculate a p-value like we normally would. What does this look like? Think back to last semester. Paired sample t-test? Independent sample t-test, right? Remember, with an independent sample t-test, we have error in sample 1, error in sample 2, which essentially doubles our standard error, right? So we've got basically standard error for sample 1, standard error for sample 2, looking at the difference between these. And so what we can then do is say, is the population coefficient, or is do I have evidence of differences in my estimate of the population coefficient for this population and the estimation for this population? See kind of what we're doing with this setup and sort of the scenarios where we might use this? Questions? Okay. In SPSS, have to do this by hand. Stata will do this for you using this core test I function here. Basically what we're doing is we're saying, all right, I've got a correlation of 0.5 in my sample of 104 in my one group. I've got a sample of 0.53 with 87 other people in my other group. Just run that, and it's going to go through and give you a test, right? So my Z statistic here is negative 0.714. My p-value is 0.475. So we'd say we don't have strong evidence of a reliable difference between a coefficient of 0.45 and 0.53 at least with these two samples. Okay. So again. Won't be relevant for most of you, but if you are someone who uses Stata or will be using Stata for some stuff, a nice way to go through and automate some of this. All right, so we see kind of what we're doing with this situation, correct? All right, another thing we might want to do, again, anytime I say, hey, tomorrow, guess what? I've got a statistically significant effect. And I don't tell you anything else. What does that technically mean when I tell you I have a statistically significant effect? Not much. It does tell me something. What does it tell me? Something not equal to 0, right? But as we talked about, a lot of times something not being equal to 0 is not terribly informative to show what I'm trying to do, right? And we don't see this a whole lot, but we can very easily. Let's say I'm running, CJ, you're doing some, let's say, motivation, personality types of things, right? And you're saying, boy, I'm expecting sort of this variable to correlate with this variable to some extent, but if it's really below some value, if it's not at least a moderate, at least if it's not a medium correlation, or let's say if it's not at least hitting benchmarks for a small correlation, if it's not correlating at least 0.1, it's really not worth sort of looking farther into, right? But this is a different question than is it different than 0? You're like, is it different than 0.1? Because if it's less, I'm not even going to worry about it, right? What we can do is we can test our correlations against some specified pre-specified value. In this case, we're saying our null hypothesis is the association between variables, the population is equal to some value R, or the association is some value with it, right? And so Howell in his text, the question is whether or not this is useful, but what this starts to do is it starts to, remember when we went back and talked about and read that Milo paper where we were talking about the differences between social sciences and the hard sciences, where hard sciences, how in physics, I'm saying my theory predicts that this value should be this. And if it's not this value, then my theory is wrong and I'm going to scrap it, right? That starts to become hard. Versus what we do in social sciences is we ask, is it 0? Well, it could be lots of things that's not 0, right? And so I think as we're starting, particularly if we have a good understanding of our area and we have some reasonable expectation of how things should relate, we can start to call our shots, we can start to make point estimates, which would be a gangster move if you put this into a paper and said, this is not 0, it needs to be at least this. And if it's not this, I'm not even going to worry about it because it's not worth screwing around with. What we can do is we can go through and calculate, test against some value that's not 0, right? What we can do is we can calculate a z statistic where, again, we take our correlation that we observe, right? And use Fisher R to Z, translate that into sort of R prime, right? And then we can take whatever our value here is, right? Let's say our hypothesized null value is 0.1, right? So I would take 0.1, so that's what I'm assuming my null value is in the population, and I take 0.1 to use Fisher R to Z, move that back, right? Then I'm taking sort of my R to Z from my observed correlation minus my transformed, whatever my null value is, in this case 0.1, divide that by square root of 1 over n minus 3. And then I've got a test, not against 0, but a test against my hypothesized value. Okay. Not hard to do, pretty easy to do. We don't see it because we're often in psychology either not sure or haven't thought about it or too scared to make a prediction because it's raised the threshold, right? I'm saying that this has to be not just not 0, it has to be bigger than 0.1, right? But again, in thinking about moving our field forward, sort of being more precise in terms of our estimates, something that might come on your radar at some point down the road. Or in terms of trying to rule out spurious effects, right? I'm looking at the relation between X and Y, and if it's something super small, I don't care, particularly if I have a large sample size, right? If a correlation pops up that's 0.1, I don't want to talk about it as a real thing because it's too small for me to care about, right? So what I'm going to do is not test against 0. I'm going to test against some value that makes sense given my study and sort of move forward from there. Very easily be able to go through. And I mean, it takes a little bit of hand calculation to put together an Excel sheet. We'll do that real quick. Questions about this? Or where this might come in handy? Okay, cool. Last thing we're going to talk about here in terms of comparing correlations, situation where we're testing correlated correlation coefficients. Oftentimes, when we're doing stuff, particularly psychometrics, right, we might be interested in comparing correlation coefficients that share some measure, okay? Sally, what are you interested in? What are you studying today?
Caregiving and culture.
Caregiving and culture. Okay. And give me a third variable.
Help seeking.
Okay. So I've got a measure of help seeking. And X2 is, it's called caregiver stress. Is that fair?
Yep.
Okay. And then X3 is culture. Okay. And I want to know if there's a difference in the correlation between culture and caregiving and culture and help seeking. Okay, so I've got one sample, right? I just got, let's say, 100 people. And I want to know, is our culture and help seeking equal to our culture and caregiver stress? Okay, I'm not sure this actually works out in terms of something that's conceptually meaningful, but I'll worry about that for right now. Okay, so I've got two correlations that I want to compare. Okay, can I use Fisher's R to Z with what we had talked about before? What do you think, Mara? What's up?
Yeah.
Okay. What's different about this scenario than what we had talked about with the Fisher's R to Z piece? Yeah. What?
No.
Go for it.
Got like variable threes and both of them.
Yeah, variables 3's in both of these, right? So before, what we were talking about, I'm looking at the correlation between hamburgers and pizza in the US and Germany, right? That's R1 and 2 for the US is equal to R1 and 2 for Germany, right? This is a different thing. These are two different samples. These are two completely different populations, right? What I've got here is I've got a correlation. I want to see whether or not 3 and 1 are correlated different than 3 and 2, right? So 1, I've got it all from the same sample, right? And then 2, these aren't dependent correlations, right? Because probably help-seeking and caregiver stress, are help-seeking and caregiver stress correlated probably? Was it?
Well, yeah.
To some extent, right? Yeah. We would expect these two things. So there's a dependency between these two coefficients, right? So what we need to do is we need to come up with a different strategy in order to go through and test these. In the test of these correlations, what we need to do is we need to account for the dependency between my two other sort of the intercorrelation between these things. Okay. I'm working on a paper right now. I want to know. I'm looking at, let's say, I've got measure X, which is my target, right? And I've got a convergent and a discriminant measure, right? And what I say is if my scale is measuring what it's supposed to measure, it should have a stronger correlation with my convergent measure than my discriminant measure, right? Just in case. So in terms of just basic psychometrics, right? That my convergent measures, this is something that in theory, my measure here should correlate strongly with this and should be sort of modestly or relatively uncorrelated with this thing, right? And so let's say I do find that. I say, all right, my measure X is correlated with my convergent measure 0.45 and correlation with my discriminant measure is 0.31, okay? And what I want to do is I want to see, okay, well, I can look at them, the absolute values are different, right? But do I have evidence that these are actually different more than just what we would expect just due to sampling variability, okay? Now, all of a sudden, I'm in a situation where these two things, so I'm going to have correlations here. They share a measure, but there's also going to be a correlation between my convergent, my discriminant measure here, right? And I need to do something to account for that. Okay. So anything else to that?
I always have had this doubt. So if you are using the same correlation to measure convergent and discriminant validity, how much is good for each one? How much is correct or proper for each one?
Yeah. And so this is a thing where this specific test might start to come in handy, right? Because I could see the correlation this coefficient here is going to measure the relation between my target measure and my convergent measure with some degree of error. This is going to measure my target measure and my discriminant measure with some level of error. And then my convergent, my discriminant measure are going to be correlated together with some sort of error, all within the same sample, right? And so what I need to have is some procedure that goes through and allows me to test the strength of these correlations, because Fisher's R to Z isn't going to work, right? I reviewed a paper the other day where they're just trying to do a bunch of this stuff, and they're like, oh, R to Z transformed everything. Can't do that. That's not a proper test of stuff, okay? So what we see is we've got this situation, right, where we've cross-sectional data measured 1, 2, and 3 all together, and we're looking at differences in the correlation. What we also might use this for is if I've got a correlation of X and Y at time 1, and a correlation of X and Y at time 2, right? We've still got dependency because then that's all sort of the same thing measured on at the same time point, right? So let's say I'm measuring 2 variables at the beginning of treatment and 2 variables at the end of treatment, and I want to see whether or not sort of they're still correlated at the same level at the beginning of treatment, at the end of treatment. Same thing, we've got dependency between that because they're sort of repeated measure stuff, okay? So, procedures for conducting these types of tests, it's sort of, there's several elements that you have to go through and calculate. It's not technically hard, you just have to make sure your algebra is correct. Howell goes through this, Steiger is a classic paper. Mang is nice because it sort of gives you a few more different options, including sort of omnibus tests and contrasts and things like that. Have you going through and reading that for this worksheet, but they go through and following the steps that are outlined in that paper. But people see kind of where this test of correlation coefficients could come into play and might be helpful. Okay, cool. All right, so confidence intervals for our effect sizes here, or for our error, or for our correlation, Pearson correlation. So talk about how our Pearson correlation is in and of itself a very, very nice measure of effect, interpretable measure of effect. What we might want to do then is start to calculate confidence intervals around that effect size, around that Pearson correlation. Because Alicia, you go through in your thesis and you say, oh, the correlation of X and the correlation of Y is equal to 0.3, right? Is that the population value? No, right? Hopefully it's close, right? But what you've done is you've estimated the population value with some degree of imprecision, right? And that's what our confidence interval is going to give us. It's saying, okay, you're going to give us a range of supported values. My best guess is that it's 0.3, but anything that from 0.25 to 0.35 would be reasonable estimates of the population based on the data that we've collected. 0.3 is still my best guess, but if you said, oh, it's 0.26, I think fine. They are not incompatible with that estimate, right? Because it's in that confidence bound. So what we can do, because we know how to calculate a standard error for our correlation coefficient, we can then easily turn this into calculating a confidence interval. So my confidence interval for my population parameter for rho prime is going to be my Fisher R to Z, so R prime plus or minus whatever my Z statistic is, whatever my confidence level is, times square root of 1 over n minus 3. Easy, straightforward, right? And so then I take what I'm going to get here is I'm going to get R prime plus the confidence bounds around R prime, okay? And so this is good, but are we interested in confidence bounds around R prime? No, we want confidence bounds around R, right? So what we need to do then is we need to take our point estimate. Well, we already know what our point estimate is because we got R prime from our original correlation coefficient. What we need to do is we need to take the upper and lower bounds of the confidence bounds around R prime, back translate that into correlation values, which will then give us our upper and lower limits for R. Okay? So again, we're just reverse engineering our Fisher R to Z transform. So we've got R, my value is going to be base E taken to the 2 times R prime power minus 1 divided by E base E taken to the 2 times R prime plus 1. Go through and do that. That's going to back translate that into actual correlation coefficients. Right? So the math isn't terribly difficult. You just want to make sure that you've done that correctly. Always when you're going through and calculating upper and lower limits with a confidence bound. If you have a point estimate that doesn't fall within your confidence bound, what's going on?
You fucked up.
Yeah, exactly. Something went backwards, something went sideways at some point, right? So always, 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 whenever with this, anything else, making sure you're going through looking at your values and saying, does this make sense, right? So people seeing sort of what we've got going on here, not too hard, right? So we can't deal with R directly, and so what we can do is we can go through Fisher R to Z transform, get an upper and lower limit with upper and lower bounds of Fisher R to Z, then back translate that into the metric that we're actually interested in using. So not that different than confidence intervals around D. Remember, we go through, we get an upper and lower non-centrality parameter that we have to back translate into a sort of a D value. Same basic principle here. Questions? All right, cool. Again, SPSS won't do this. Stata will go through and give you confidence intervals around Pearson correlations. If we go pairwise correlation, so we just get correlation between a measure of PTSD and so on, right? And if we tell Stata CI2, same measures, and then say we want a correlation, it's going to give us the confidence bounds around this estimate. So we see correlation is negative 0.23 on 226 observations. Here's the lower limit, the upper limit. So it's just a program that'll do it for you, right? Same thing if I just put in, let's say I don't have actual data, I just want to run an estimate. And I can say, all right, instead of CI2, say CI22 for 226 observations, correlation of negative 0.2307, and it'll sort of, without actually having the data, it'll just calculate it for me here. So again, it's giving me the same thing, same confidence bounds here. So it's nice again if you're just using Stata to do this quickly. All right, power analyses for Pearson correlation. This is easy in G-Power. Sean Ignacio, have you used G-Power before? Okay, cool. Sean, you haven't? Okay. It's an easy program. Just download it. It's free. The lab sort of works pretty slick for basic power calculations. On the interface, what we're going to do to get a power analysis for Pearson R, we're going to, in the test family, we're going to select exact correlation bivariate normal model, and then the two tails and all the stuff we would normally put in, and then we'll go through and give us our power analysis.
What is the probability of making which type of mistake?
What's that?
Error type what is the probability? Power is the translated as the probability of making type 1 error or type 2 error.
Type 2 error, right? Again, thinking about power as the long-term probability of rejecting the null when the null is false, right? And so we generally want that to be higher, right? Type 1 error is like me saying that there's something there when there's not, right? Rejecting the null hypothesis when the null hypothesis is true. Probably in psychological statistics, type 2 errors are far and away the far more common errors and probably should be more concerned about. But yep, we go through and do that. So here, we've got my correlation. So I'm expecting a population value of 0.3, so a medium effect in the population, so moderate correlation. Error probability is 0.05, powering to 0.80. My null value of the population is 0, right? And it looks like I need a sample of 84 individuals to have adequate power to test for the population effect of 0.3. Questions? People kind of remember how to navigate G-Power stuff? Correct. Okay, cool. Going to finish up with some different types of correlations, variations on our Pearson correlation. First version is going to be called, what's known as our point by serial correlation. Okay, point by serial correlations are correlations that we're going to calculate when we're looking at the relation between a dichotomous X value and a continuous Y outcome. And these are all correlations. You can sort of flip-flop them around, doesn't matter. Sort of one way or the other to think about. So we've got a dichotomous X and a continuous Y. Okay. In this situation, my point by serial correlation is mathematically equivalent to my Pearson correlation. There's no distinction. I'm not going to get a different value if I run a Pearson correlation or a point by serial correlation. Technically, if I look at an association between a dichotomous variable and a continuous variable, it's going to be, I'm technically running a point by serial correlation, but the value is going to be the same thing as Pearson correlation here. Okay. So mathematically equivalent. Again, if I'm looking at, in this graph, I've got people who sort of following a motor vehicle accident. Do they experience chronic pain? Do they not experience chronic pain? Right? So my X variable is dichotomous. It's either 0 or 1. My outcome here is PTSD, right? And so what I've got here is my distribution of scores for individuals with no pain. Here, my distribution of scores for individuals with pain. So what we see is that when X equals 0, my expected value of my Y is going to be the mean of Y. When my X value is 1, my expected value of Y is going to be the mean of group 1 here, and my correlation line or my regression line is just going to go through the mean of those 2 points. So if I go through and I square my point biserial correlation, this is going to represent the probability or the proportion of variability in my outcome variable that's attributable to my grouping factor. Okay. And so what does all this sound like? This scenario, Chris?
Like what is it really similar to?
Yeah.
T-test?
A t-test.
Independent stable t-test?
Yep. My point biserial correlation is mathematically equivalent to a t-test. Okay. What I've got is I've got one variable that's a dichotomous variable, one variable that's a continuous variable. The significance test for my Pearson, or so my point biserial correlation, identical to that for R. So I'm going to test this the same way I test a Pearson correlation. So it's just my point biserial times n square root of n minus 2 over square root of 1 minus the square of my Pearson, or my point biserial correlation. Again, the value at a t distribution with n minus 2 degrees of freedom, exact mathematical relation to independent samples t-test. Okay. So I've got, if I take the square of my point biserial correlation, is going to be equal to, if I take it in my t-test, if I ran an independent sample t-test, and I took my t-statistic and squared it, divided by the square of my t-statistic plus the degrees of freedom, it's going to give me the square of my point biserial correlation here. Okay. So we're just, they're equivalent tests. We can move back and forth either way. Okay. So as a consequence, interpretation of my means-based tests and my Pearson or my point biserial correlation are going to be identical, right? So I can look at men and women differing in weight, right? We know that men and women differ in general amounts. I'm sorry, as you defer to the expert, he says that's an old wives' tale. It's a common misperception, right? So I could go through, and if this is my question, I don't want to see look at gender differences in weight. What are we typically going to use? Independent sample t-test, because that kind of makes the most sense, right? But I could also just run a correlation between gender, or between sex and weight, and I'm going to get the exact same thing. It doesn't matter. They're the same test. We talk about it a little bit different, right? So I can talk about this as the association of sex and weight, or I can talk about it as differences in men and women in weight. It's all the same thing. Mathematically, it doesn't matter. I can talk about it either way. The only thing that depends is how I want to talk about it, what makes the most sense, right? So if I wanted to, if this was a primary outcome in my study, I might want to talk about it in terms of a mean-based difference, because that's kind of easier to think about, right? But if I wanted to talk about it as an association between sex and weight, that's perfectly acceptable too, right? If that's not something that's super important, right? Pearson or biserial correlation is easy to just kind of report back. Yep, these two things are associated with one another, and call it good from there. Okay? So it doesn't matter. So we can also say that men and women differ in weight. We can say there's a linear relation between gender and weight. We can say physical weight varies with gender. All of these things are reasonable ways of talking about this. The only thing that determines which one is maybe the best choice is your conceptualization, how you're wanting to present these results. Okay. So the Pearson, or the point biserial correlation and your independent sample t-test, identical. Okay. Got in fights with people about this. I'm like, just give me a correlation between grouping variable X and some outcome. They're like, well, you have to use a t-test. You really don't have to use a t-test. Just give me, I'm not trying to spend a bunch of time talking about mean differences. I'm just going to report association. Right? They're mathematically equivalent, right? There's no difference between the two. So, yes?
So when would you want to use a point biserial correlation instead of an independent sample t-test?
Depends on what, if I'm looking at, if I've got 5 different correlations. So I've got, let's say, I've got a bunch of continuous measures. I'm looking at the measure association between X and Y, a bunch of continuous X's, a bunch of continuous Y's, and I have one variable in there that's dichotomous. Do I really want to talk about all these correlations and then switch over and start talking about mean differences? It's bulky and clunky, because I don't need to. I just want to go through, I can frame the whole thing and talk about, this is the association between sort of these different variables, right? And that might be sort of a way to go through and do that, right? If sort of this is a big kind of piece and I want to talk about mean level differences, which can be easier for people to vision. People like groups, right? This group is bigger than that group, right? Then maybe I want to talk about it that way, but I don't need to, right? I can present that however I want to present that. So if we go through and we take a look at, here we're looking at, again, sex and PTSD in this sample of 337 people. We see that my Pearson correlation, which is actually my biserial correlation, SPSS labels that are Pearson, do my point biserial and my Pearson correlation are equivalent, they're interchangeable. Really what I've calculated is point biserial, but it's kind of a semantic issue. But my significance here, my p-value is 0.084. If I go down through and I run the same analyses with an independent sample t-test, I get my t-statistic of 1.733. Again, my significance values 0.084. They're the same thing. It's the same thing, just kind of in a different presentation. Up to you how you want to go through and present that. Comfortable with this? Okay.
Good.
Yep.
Go back, please. So the significance that we will consider is in the first row or the second? Equal variance, yes.
Okay, so this is good. So if we go through and we look at Levine's test, so this is telling us whether or not we have a violation of homogeneity of variance.
Yeah, that
right?
is.
And so here we see that we don't have strong evidence of a violation of homogeneity of variance, so we're just going to go through and account for this first one here.
Okay, the first one.
Yeah. Now, if that was some value that suggested potentially that the variability of PTSD scores was different in men versus women, we'd probably go down and look at the corrected test down here. All right. Same thing in Stata, right? Here's correlation between sex and PTSD, independent sample t-test. We're saying that our two-tailed test is identical in the two. It's just a different way of presenting the same information. Okay. In terms of effect size, as we might expect, our point biserial correlation, direct association with D, just like our Pearson correlation did. I can calculate D based on my Pearson or my point biserial correlation. What I can then do is I can calculate confidence interval or confidence bounds for D based on the T statistic that is associated with my point biserial correlation. Right? What I want you guys to recognize here is that if you understand the association between these, I can start to move back and forth easily between sort of one metric versus another for the purposes of my study. Right? Tomorrow you're working on your thesis, and you've got a study that sort of reports things that it's not in a metric, that's sort of how you want to talk about it. What you can do is take this and start to move back and forth to calculate whatever intervals you want to do because you understand sort of the relation between these, right? So if, let's say, someone has reported a point biserial correlation or just a Pearson correlation between the dichotomous variable and the contiguous variable, right? If I know what the sample size is, I can take that point estimate, I can calculate a t statistic, and I can take that t statistic and I can get non-centrality parameter, upper and lower bounds using some procedures we used last year, and I can calculate an upper and lower bound of D, use my the estimate of the point biserial correlation to calculate a D, and now I've got an interval estimate, a point estimate of D and interval estimate around there, right? And so they're looking at the association between a grouping variable and some outcome, right? But I want to think about this in terms of standard deviation difference, right? What I can do is I can take their correlation that they reported, I can back translate that into a D statistic that's going to say it's a D of 0.53, right? And I can say, okay, there's about a half standard deviation difference in mean of this group versus the mean of that group. Right? Half standard deviation increase for here versus here, upper and lower bounds. Can go through and do that and move back and forth interchangeably. Yeah.
So in SPSS for the partial point biserial correlation, where do you click? Because you have the Pearson, Kendall's tau, and Spearman.
Okay. Doesn't matter. Do I need to specifically request a point by serial? No, why not, Chris?
Because it's interchangeable with the Pearson code.
It's interchangeable. So as long as I'm,
Yes.
yep. So as long as I'm looking at correlations between continuous and continuous variables or continuous and dichotomous variables, don't have to worry about it. I just drop it in there and it's just all going to go through and pop up the same thing. My coefficients won't differ. It's a good question. Questions on any of this? Okay, cool. Other thing we're going to finish up with, talk about a phi coefficient. Okay, phi coefficient, phi is the formal test of a relation between a dichotomous x and a dichotomous y. So now instead of a dichotomous x and a continuous y, I've got two dichotomous variables, two 0 1s. Always, always, always code your dichotomous variables as 0 1s. Don't do 1, 2, and screw stuff up. 0, 1, okay? But what's nice is that our phi coefficient, also mathematically equivalent to our Pearson correlation coefficient. So we're good here, right? We know that our sampling distribution of our phi coefficient is going to be a function of our chi-square with 1 degree of freedom. And so my phi coefficient, if I take my chi-square value over the square root of my chi-square over my normal people, my sample, you can give me a phi coefficient. Again, just like our point by serial and t are interchangeable, interpretation of my phi coefficient, my 2 by 2 chi-square interchangeable. So back and forth, same thing, okay? So I can talk about, I've got two variables. I've got,
ADHD, yes, no, and pass, fail, and a grade.
awesome, thank you. ADHD, yes, no, pass, fail, and a grade, right? I can talk about this as the association between ADHD and pass, fail, right? Or I can talk about this in terms of whether ADHD diagnosis is independent of passing, failing, or passing, failing is independent of ADHD diagnosis. You can work back and forth. It's all the exact same thing, okay? So again, if I go through and I take a look at my correlation between, okay, what I've got here, I've got, again, participant sex and PTSD diagnosis, yes, no, right? What I see is I got my correlation. This is technically a phi coefficient, right? And my significance here. Or if I run this as a crosstabs, as a chi-square, I've got my significance level is, I guess it's a little bit different here, but functionally identical. Request a fee. But if I were to request within chi-square, ask it to give me a phi coefficient, it's going to give me a value of negative 0.014 here too. Okay. So just showing same thing in Stata. Again here, correlation between sex and CAPS PTSD diagnoses. If I run crosstabs, it's going to give me my significance value. Again, it's sort of rounded a little bit differently here, but the same type of thing. Okay. So Ignacio, same type of thing. As long as, in SPSS, as long as I'm interested in the association of any combination between dichotomous and continuous variables, I don't need to worry about anything. I can just go through and drop those into just the bivariate correlation things, and it's just going to give me everything. It's going to be interchangeable. So I don't need to specifically request, oh, give me a phi coefficient, or give me sort of so on and so forth. Okay. Now, remember that this phi coefficient is specific to a 2 by 2 chi-square. Now, if I have a categorical variable that has more than 2 levels, then I'm looking at some sort of other measure of association. But for the 2 by 2 case, equivalent to Pearson R, point by serial, equivalent to Pearson R, making that our t-test, equivalent to Pearson R, being able to move back and forth between them and knowing that sort of I can go through and do this. Questions about how we can go back and forth, talk about Pearson, how point by serial, fees, sort of testing correlations, any of that stuff. Okay, cool. Other coefficients, so not now, sometimes we'll be interested in associations between things that aren't continuous or dichotomous, and then we get into some other types of things. Not my point by serial, but my biserial correlation. This is going to be similar to my point biserial, but we're assuming some continuity in my dichotomous X, right? So let's say that I have, diagnosis, ADHD diagnosis is a good example. Diagnosis, this is meeting diagnosis. Do symptoms of ADHD occur as a sort of either you completely have them or you completely don't? No, it exists on a continuum, right? And so what we've done is we dichotomize that, it actually can attenuate that association. If I was looking at the association between ADHD diagnosis and continuous GPA, right? What I might do is say, well, I know that my dichotomous diagnosis variable is actually a continuum and not actually a dichotomy. And so what I could do is I could run a biserial correlation, and that's going to give me technically a more, probably a better estimate of sort of that if I'm assuming that my dichotomous variable actually exists on a continuum. Okay. A tetrachord correlation, similar to phi, but we're assuming continuity in both x and y, right? So I'm looking at what I've measured is two dichotomous variables, but I think that these two dichotomous variables actually sort of represent a continuum. I'm looking at the correlation between depression diagnosis and PTSD diagnosis. Well, I know both of those things exist on a continuum, right? So we're looking at a tetrachord correlation there. Spearman's rho, here we're looking at Pearson formula to rank the scores. Okay? If I've got something that's not actually continuous, right? What's actually ordered categorical data, where where 2 is bigger than 1 and 3 is bigger than 2, but not all by the same amount. Right? We can start looking at Spearman's rho, Kendall's tau, alternative to Spearman's rho. A little bit better estimate here. Chi-square test for linearity. If I've got a chi-square, but I've got ordered variables, so instead of CJ running a study where you've just got 3 levels of this randomized condition and 3 levels of it where there's no real order. If I actually have some sort of ordered condition, chi-square test of linearity is good. Kendall's coefficient, if I've got multiple readers, it starts to get into interreg or reliability stuff. Again, an experimental setting, I'm running some sort of behavioral code on some sort of outcome, right? This might be something worthwhile looking at. So the thing here, lots of different options. All of this breaks it back down into thinking about levels of measurement, right? So we've got our construct that we're thinking about, and then we've got how we've actually measured it, right? So wanting to, as we're going through and sort of setting up studies and thinking about how we want to analyze things, thinking very, very carefully about what did I measure, how does this represent the construct, and then maybe think about, is there an alternative that might be better than just dumping everything into Pearson correlation. Pearson correlation is nice, it's easy. And if you wanted to go don't switch over to something just to be fancy. You want to have a good reason for sort of deviating. Pearson correlation works fine for most things, right? But if you have a strong rationale for saying, actually, this is going to be better measured, or conceptualizes sort of a certain level of measurement, then we have other options for that. Okay. Questions? All right. Pretty good. We'll call it, let's do a break here, and we're not going to jump into matrix algebra. I told you that. We'll roll right into repeated measure stuff when you guys get back. Cool. All right.
Door part of the
Yeah.
video.
Oh, I can do that.
You want to hit it? Oh, awesome. The door.
The other door.
Well, you meant the door to YouTube, right? This is a semantic issue.
Does it get better in March, or is it like, is it gonna stay like this until like summer?
Yeah, it snowed in July or June last year, so temporary. It's just like a quick. It's sort of nominal, right? But the issue is like Wyoming spring. Like Wyoming, we still get like the same precipitation, except it's not rain. It's just snow that comes in, right? So like that, like I'd say it's a coin flip during graduation week on whether or not we're going to get snow. It's actually not. It's probably more likely to get snow than not get snow. But then it'll like hit like 60 degrees the next day, and then it all melts away. So it's just it's variability. It's much more variable than you might get somewhere else.
My gauge for spring is going to be when the street that I live on completely thaws out.
Oh,
So it's gonna be like midway through summer.
Yeah, it could be.
Probably spring.
All right. Gonna jump into repeated measures ANOVA stuff, okay? So, we can go through, gonna do a quick review of our means-based test. We already kind of went through that, so we'll click through that pretty quick. Talk about repeated measures ANOVA designs. Talk about a one-way repeated measures ANOVA is sort of a way to ease into this. Follow-up tests. This is probably going to be the biggest thing that's sort of difficult to figure out how we're going to go through and pull some of these apart, and then finish up with our mixed factorial designs for our repeated measures analysis. So again, basic ANOVA. We talked about this very first lecture, thinking about our ANOVA models as a test of the extent to which we're seeing whether observed differences in individual samples representing different populations are more likely the result of systematic differences in those populations, or whether or not those differences are just what we would expect just due to sampling error and sort of variability, right? So again, with our basic ANOVA model, the differences that I'm seeing in sample 1, sample 2, sample 3, 1 are the result of just random fluctuation, right? The mean level, the mean value of population 1, population 2, population 3 is all the same, okay? The differences that we're seeing are just due to sort of just random variation. Or what we're seeing here may be due to systematic reliable differences in respective populations. So population value in 1 is different than population value 2 is different than population value 3, and what we're just seeing here is that being manifested in our actual samples, right? So our test is trying to tease apart these two differences, right? Again, our hypothesis is for our null for our one-way ANOVA, means the population from which the sample was drawn are equal, okay? There's no relation between my grouping variable X and whatever my outcome is Y, right? Because in a one-way ANOVA, Chris, how many IVs do I have if we're talking about it in IVDV?
2, 1.
Yeah, which one is it?
Jeez, I think it's 2. I think it's 1.
Why is it 1?
Because you didn't really respond when I was saying 2.
Guessing, right? Someone help them out. Why do I use a one-way ANOVA? Why do we only have one? Why do we only have one IV?
It's one way.
Well, it's one way. It's
Okay, never
give me
mind.
smoke and mirrors answers here. But yeah, it's just a grouping variable, right? We've got a grouping variable. So our grouping variable, our variable is just a condition. We've just got different levels to my condition, right? I've got condition 1, condition 2, condition 3. So I'm just really, even though, and this is where it can get confusing, right? Well, I've got 3 groups, 4 groups, so on and so forth, but I've only got one variable. Variable is just condition. It's a categorical variable with 4 levels, 3 levels, 2 levels, something like that, okay? So we're saying that there's no relation between our grouping variable and our outcome. This is just a different way to talk about this within a kind of like a GLM framework, right? Talking about the association between condition and my outcome. Or I can talk about it as differences in levels of my condition across my outcome. Our alternate hypothesis is that at least one population mean differs from the rest, okay? Do we have a way to state our alternate hypothesis in statistical notation? No. Why not?
Because you can't, because there are more than one groups or 2 groups that you can't.
Perfect.
This is equal to this or this.
There's lots of different ways. It would be, you know, you could put 1 is not equal to 2 is not equal to 3. That's one way that could look, but it could also look a lot of other ways, right? 2 could be equal to 1, but not equal to 2 could be equal to 3, but not equal to 1. 1 not equal to 3, but both equal to 2. All sorts of different ways going on here, right? So we say at least one is different, okay? And we would say that these data are unlikely. If we were rejecting all hypotheses, we say that these data are unlikely, assuming equal population means, okay? Our F statistic is our test statistic here. Think about our F statistic conceptually as the variance between samples over the variance expected if the null hypothesis were true, right? So even if there is no difference, the null hypothesis is true. The population mean 1 equals population mean 2 equals population mean 3. Alicia, are we going to get the same value in our sample for each one of those samples? No, they're always going to be different to some degree, right? So our F ratio is saying, is the variability that we see across these samples, and what is variance code for in ANOVA land? guess though, like technically not an incorrect guess.
Sticking with it.
Right? But if we say variability, it means what are we talking about?
That the difference can be kind of.
Differences, right? Variability is just differences, right? If we've got two sample tests, then we talk about just differences in group 1 and group 2. If we've got multiple samples, we can't talk about like difference, but what we talk about is variability, right? So here in set 1 and set 2, Sally, which one of these sets 1 or sets 2, which one of these are we seeing more differences in the means?
Set 1.
Set 1, yeah, how do you know that?
Because the first mean is 20 and the third one is 35.
Mhm,
And so
right.
there's a lot of variability.
Right, so we've got more differences, right? But we can go through, if we go through and we calculate the variance of those means, we see that this variance is larger than this, right? So our variance is just it's a metric of the differences that we're seeing across these scores, okay? So when we're saying variance in ANOVA mode, we're just talking about differences, okay? And so again, our objective here is to parcel out the variability in the sample across between treatment variance or between group variance, within treatment variance, to try and tease out these systematic differences. So, our differences between our groups. Possible reasons, right? One, we have different systematic differences because of some sort of effect, right? Population 1 is different than population 2 is different than population 3. What we're seeing is differences in our group means because these populations truly are different. But we also have differences that are going to be due to random non-systematic differences, right? This is going to be just individual differences across our participants, experimental error, just kind of random variation and stuff. We're also going to see systematic differences that aren't related to our grouping factor. Treatment 1, treatment 2, and treatment 3, or group 1, 2, 3 might be all different for some reason other than what we've measured. But if we haven't measured it, where does all that variability go? CJ?
Error.
Error, exactly right, sir. Right? If I didn't measure it, I can't account for it. Even if it's systematic, it's still going in that error term because it's not something that I've accounted for, right? All right. Sally, where are we seeing, you're on a roll of variability, where are we seeing between group differences in sort of this set?
Or no.
Yeah, so which sets of means are we looking at it between group differences?
Oh, so you're comparing the different treatments.
Yeah, right, so down here,
Mhm.
we're looking at between group stuff. We're seeing like, what are the differences between treatment 1, treatment 2, treatment 3 in this stuff? That's where our between group stuff is happening. Contrasting this with our within treatment groups, okay? We're saying, once again, that everybody in each one of these conditions are receiving the same procedure, okay? So Sean, if my grouping factor, in this case, so we're looking at learning performance based on room temperature, right? If the only thing that determines performance on this test is the temperature in the room, that's the only thing that determines performance, what should all the individual scores be within treatment 1, and treatment 2, and treatment 3?
They should all kind of be the same.
They should all be identical. If room temperature is the only thing that causes differences, then these should all be identical, but they're not, right? So we have the mean value, right? And so the only thing that caused differences in performance was temperature. All the values here should be 1, everybody's performance here should be 1, everybody's here performance is 4, everybody's here performance is 1, right? And so because we see that not all those values are equal to sort of the mean values, what do we call deviations within treatments from the mean value?
Oh, your error.
Yeah, it's just error, right? It's unaccounted for. It's stuff that I haven't accounted for, right? And so what we're seeing in our within group differences, right? All of these differences that we're seeing within that group are due to something that we haven't measured, right? They're attributable to individual differences just because people are different than other people. It could be experimental error. We don't know why things are going on within those treatments or within those groups. So right here, when we're talking about our within group, within our differences in scores within an individual group, this is what we're looking at. We're looking at variability within. And our variability within is called what, Nick?
Error.
Error, exactly, okay? Now, just because it's error doesn't mean it's not random, right? There could be things that are going on within groups, say personality stuff, motivation stuff, sort of engagement with whatever condition we're doing, right? But if we haven't measured it, we can't account for it, and so it all gets chunked up into error. All right. So if we're thinking about this in terms of our F ratio, how this breaks down, our F test is comparing these two types of variance. We've got our between treatment variance and our within treatment variance. So conceptually, if we're thinking about what's going on in these statistics, we've got our observed differences across our groups over the differences that we would expect just based on the sort of just the null has true, and we're just seeing random variations here, right? We can also think about this as our observed group differences are going to be a function of systematic effects plus random differences in other garbage that's going on over random differences in other garbage that's going on, right? And in the case where there's no systematic group difference, right? The variability that we're seeing across groups is entirely attributable to error. Probably what we're going to see is no effect here, plus random differences and other things that are going on over random differences, right? And so we're going to get an F value that's probably close to 1, right? But if there is a systematic effect, what we do is we add that systematic effect in, and so we've got our systematic effect plus random differences in error. Over the top of random differences in error, these two things are going to cancel out, so whatever that systematic effect is going to start to force that F statistic larger and larger. We're going to start to get something that looks more like evidence of something systematically different across these groups. Okay. So kind of flew through that. It's kind of a recap. Questions so that people understand conceptually how we're, within an ANOVA model, how we're partitioning variability to start to get a sense of a signal within this stuff. So, for our ANOVA, right, and this starts to become important how we're thinking about teasing this stuff apart. We've got our sum of scores total, okay? Sum of scores total, this is the total variability in our set of scores, right? And we're going to calculate this by definition. Our sum of scores total is going to be the sum of the squared deviations of individual scores from the grand mean here, okay? So we're going to take into the deviation of individual scores from the grand mean, square that, sum it all up. CJ, why are we squaring these values?
So that they're positive.
So that they're positive, and so what doesn't happen?
They're not negative.
They're not. No, they're not negative. What happens if we don't?
Oh,
what
zero.
happens? What's that?
So it's not 0.
Yeah, so it's not 0. So we have to square these, because otherwise the positives will cancel out the negatives, and by definition, we'll just have 0, right? So what we do is we have the sum of the squared deviations of individual items from the grand mean. This is all the variability in the sample, okay? So if you were to take all of these scores and calculate the variance of all of those scores, this would be your sum of scores total. We're also going to calculate the sum of scores error. This is a variability within each condition or group, okay? What we're going to do is we're going to calculate, this is going to be the sum of the squared deviations of individual person in group J minus the mean of group J, squared that, right? So we're going to have 0 minus 1, 1 minus 1, 3 minus 1, 1 minus 1, 0 minus 1. We just square those, add those up, and then take 4 minus 4, 3 minus 4, 6 minus 4, so on and so forth. Add that up. So our sum of squares error is going to be the variability within groups due to individual differences, different types of error, and things along those lines, right? So this is basically our estimate of what we would expect just due to random variations, due to things that aren't accounted for in our model. And we have our sum of scores treatment, or our sum of scores groups. This is the variability or differences with across each condition of the group. What we're going to do is we can calculate this as the sum of the squared deviations of my group mean minus the grand mean, right? Times the number of people in each cell. Or I get this by subtraction by taking my total, subtracting my error. What's left over is just my variability between we do is we can take my variance between groups, take my sum squares treatment, divide it by my degrees of freedom treatment, gives me a mean squared group or mean squared treatment. Same thing, error, sum squares error divided by degrees of freedom error gives me a mean squared error. In ANOVA speak, what is mean squared? What is a mean squared?
It's like the thing when you have a box, you know, that you add them and then you add the last one.
Yeah.
Is it standard error?
Not standard error. Standard error is, remember, standard error is just a property of your sampling distribution. Okay. What is mean squared code for? It's a variance estimate. That's all it is. You got a sum of squares divided by your degrees of freedom. Take a sum of squares divided by degrees of freedom. It's just variance, right? And this can be confusing because as we go through and we start to think about things, there are times when we want to take that mean squared error from our ANOVA table and use it for different stuff. Mean squared treatment is just your variance across your treatment means. Mean squared error is just your variance within groups, right? So remember this, because otherwise back, oh, mean squared, that's a weird computational statistic that sort of is different. It's not. It's just a variance estimate. Okay. That coming back to you, kind of remember that. All right. And then our F is our between group variance over our within group variance. It's our F statistic, right? As that's increasingly larger than one, then say increasing evidence for systematic differences across groups. Okay. So. Conclusions, interpretation. So in our, again, this is an example from last semester. We've got our sum of squares between, sum of squares within, our sum of squares total, our degrees of freedom, our mean square, which is our variance estimate, our F statistic here, right? So here, my hypothesis, my null is that the mean temperature for my 50 degrees is equal to 70, is equal to 90. My alternate is mean learning scores will differ in at least one temperature. I'd flag that and tell me to sort of put a population, sort of make sure you're referencing population in there, right? But in terms of conclusions, right? So for Sean and Ignacio, sort of thinking about, talking about and interpreting these effects without relying on, sort of falling back on significant, not significant language, sort of trying to fill things out a little bit, right? So we might say here, results of the study provide strong evidence against the null hypotheses of equal performance across temperature conditions in the larger student population. Okay, so what I've done is I've said, framing my results in terms of strength of evidence, right? And Nick, how do I know that I have, so I've said I've got strong evidence. How did I, based on sort of the statistics that I reported, why did I conclude strong evidence here?
Depends on what you're looking at, but you could look at the S value, the base factor down, that value, they're intertwined.
And can you give me, so there's a lot of things going on, right? So I've got a p-value 0.002, right? Think about p as evidence of, a measure of continuous evidence against the null. 0.002 is decent, right?
It's the coin flips, right?
Yeah.
Yeah. So seeing the results that we have given these data, the projecting the null hypothesis is 9 times. Wait, that's the base factor now. It's similar evidence as to seeing a fair coin flip with the heads 9 times in a row.
Yeah, right. So basically, if I'm looking at this and think about this in terms of evidence against the null hypotheses, right? Ignacio, if I said, hey, I've got a fair coin, let's sort of flip for money, right? And I went through and I called heads 9 times, and 9 times heads came up. How convinced would you that I had a fair coin? Starting to become pretty suspicious, right? 9 heads in a row. I'm starting to get. Are you 100%? Like, are you gonna like bet your house on that? Maybe not, but I'm starting to become fairly convinced that probably what I'm dealing with is probably not a fair coin, right? Same thing with the base factor bounding. In best case scenario, which is never the case of what we're working with, but sort of best case scenario where before we collected these data, the null and the alternate were sort of equally likely. These data would say that the odds of the alternate hypotheses are about 30 times that of the null based on the data that we've collected, things along those lines, right? So also looking at my omega squared, right? So based on the data we've collected, we're thinking about 58% of the total variability in performance is attributable to temperature condition here. That's massive, right? So compelling evidence against the null hypothesis in this situation, right? So just trying to go through, you'll notice we go through, have a lot of information contained within this without ever talking about what's statistically significant or not, ends up being arguably a more informative way of talking about this, right? But we say despite evidence of at least one differences in at least one temperature condition, results should be interpreted within the context of the small sample. Right? We've only got 15 people, we've got 5, and 5, right? So we want to be super careful about sort of putting too much in. Yeah, data looks compelling, but we also have an incredibly small sample. We know that incredibly small samples lead to massive overconfidence in what we've found is real and sort of replication issues, so we want to take that into account. Okay. Questions in terms of this? Okay.
BFB, what did you call BFB?
It's a base factor bound. So one of the papers that I had sort of given to you to go through and take a look at, sort of some of the other stuff, it goes through, talks about that. So definitely go back through the old slides, sort of in that email, so go through, take a look at that, so you have a general sense of the base factor bound, so what that's doing. All right. Other thing too, so what I've done, sort of, because this is, I'm asking you to interpret things in a different way than is often commonplace, and they'll be like, oh, we just identify this as a significant difference and move on, right? So we're sort of framing this a bit differently. Work through what I don't want, and so this is often sometimes in statistics courses, people say, this is the template, use this template. I don't want you to use this as a template, because if you use a template, it doesn't let me know that you understand what's going on. It's just saying that you compare it backwards. So as you're going through and writing up in your stuff, giving these is kind of an example of how you might sort of put this together, but you know, don't use this as gives you an idea of how you might construct a response or an interpretation, but yet don't copy and paste sort of this type of stuff. I know that sometimes people will say do that, and I'm telling you not to do that, right? So just want you to play around with different ways of interpreting things to help sort of some that understand. Okay. All right, questions on our interpretations here? All right. So Lisa, we've identified evidence against the null hypotheses here, right? So we're saying that temperature condition differs, or sort of performance differs across temperature condition. Is this telling us all we want to know? What else? What are we lacking here?
It doesn't tell you which temperature is causing that difference.
And be careful with causal language, but we're not saying what, this just tells us there's a difference in there somewhere. We don't know exactly where that difference is occurring without some follow-up tests. So, people sort of up to speed, sort of comfortable remembering what we were talking about in terms of our one-way ANOVA models. Cool. Okay. A review of our repeated measures designs. With our repeated measures, what we're doing is we're assessing the same group of participants in one or more variables across 2 or more occasions. CJ, what's the asterisk here referring to? When else can we use repeated measure statistics?
We're forgetting that one that we used that had something to do with like pets or whatever. And the 2 groups were just similar.
Yeah, they're similar. What do we call that?
You can match the subjects.
Match subjects, match design. Right? So we can use our repeat measures with a match design here, right? Benefits of our repeated measures design, sort of falling into some things that sort of phenomena that sort of occur naturally, that sort of starts to map onto. It's a nice way of looking at things that maps onto how the phenomenon we're often interested in. It's more efficient, increased ability to control, account for random error. So all very, very good things about our repeated measures designs. But if we're worried about carryover effects, right? If I'm, let's say, so looking at, again, CJ's doing motivation intervention or something like that, like, okay, sort of like saying, sort of stated preferences or sort of intention, motivations and things like that. So, okay, use this for a week and then see how it impacts your stuff. And then we come back in the second week, you're back, okay, forget about all that. Now, don't do that, and we'll see what happens. It's not a reason, because we already taught someone to do something, right? We're going to get carryover effects, and so that starts to become problematic, right? So we've got some design, so depending on what we're wanting to look at, some limitations there. They're more, start to become more complex models in terms of assumptions, increased analytic complexity. We're going to go through and address that stuff so that you all can use these designs carefully. And again, for the types of experimental stuff that we do in the studies that we do, anytime we can include a repeated measures factor in there, it's going to skyrocket our power. It's going to be much, much more efficient design. Okay. So our simplest case of our repeated measures is going to be our paired sample test. Again, paired sample, we're going to examine change in scores within individuals across repeated measurements. So our question here is, what is the mean difference score in the population, right? So our difference scores are a unit of measurement for our paired sample T, right? So we're going to measure values at time 1, and we're going to measure values at time 2. Tomorrow, do I care about values at time 1 and time 2? What's that?
In what sense?
If my test is a paired sample T, right? Do I really care? Like, is my focus going to be on what's going on in time 1 and time 2? Not really, right? I'm only interested in time 1 and time 2 to the extent that allows me to calculate a difference score. The difference score is going to be my primary issue, right? So in terms of thinking about assumptions, if I've got a nasty distribution at time 1 and a nasty distribution at time 2, is that necessarily problematic? No, because my difference scores are normal, cool, no problem there, right? So what we're looking at here is the mean of the difference. So my null hypothesis here, the mean of the difference scores in the population is 0. My alternate hypothesis, mean of the difference score, is some value that's sort of not 0, sort of plus or minus. So again, with our paired sample test, what we're really asking is whether or not the difference scores that we're seeing across multiple assessments, are those sufficiently different than 0 for us to assume that the population value for the difference score is something that's probably not 0. Coming back to people. So for our paired sample set, our t-test is going to be our observed difference score minus our value observed under the null. Value observed under the, or expected under the null is 0, so that kind of just goes away. Over the standard deviation of my difference scores, my standard error is going to be the standard deviation of my difference scores over the square root of n, right? Again, my standard error of my difference scores is my expected deviation of the mean, assuming that the null hypothesis is true. Okay? So again, if I go through and in the population, the mean of one, or sort of the mean of the difference scores across repeated measures is actually 0. So the population mean of my difference scores is 0, right? But again, I get a sample of 50, right? And in that sample of 50, at least I go through and I take the difference between time 1 and time 2. If the population value is 0, what's my sample value likely to be?
Whatever that score is.
Well, yeah, so I've got time 1 and time 2, and for the sample I calculate the average difference score in the sample. Is it going to be exactly 0? No, it's going to be something, right? So it's going to be, I'm going to get a sampling distribution of that difference score, right? And so what my standard error, my difference is saying, like, how much variability am I going to expect in that sampling distribution, right, relative to sort of my sample size and so on and so forth, right? And so, Sean, what happens to my standard error as my sample size starts to increase?
It goes down.
It goes down. Why?
Because N is the denominator.
Right? Mathematically, because that N's getting bigger, right? It's going to drive down that standard error. Conceptually, CJ, why is my standard error getting smaller?
It'll be closer to a normal distribution for the population.
Right? So again, as my sample starts to get larger and larger, my estimate starts to get more and more precise, right? If I've got a sample of 20, how precise is my estimate of the population value? Not at all, right? If I have a sample of 500, that's starting to get pretty tight, right? And so, both mathematically and conceptually, we see as our samples increase, our precision of our measurements get much, much better. But mathematically, we can see as that number starts to get bigger and bigger and bigger, starts to drive down that standard error, right? So, if I'm going through and I'm taking a look at my data here, so a small set, 4 scores. I've got measured assessment at time 1, assessment at time 2. What I'm really interested in is the different scores, right? So we run our independent or our paired sample t-test in SPSS, some other statistical software. What SPSS is doing is it's calculating a vector of different scores and then just calculating the mean difference and the standard deviation of the different scores there. Okay? So again, I can have lots of variability at time 1. I can have lots of variability at time 2. But if everybody is changing about in the same magnitude, in the same direction, the standard deviation by different scores is going to be quite small. Okay, so that's kind of the quick run through of our tests that we, sort of basic tests, univariate tests that we worked on last semester. Questions? People, this coming back to people in terms of conceptually what's going on with our stuff? Okay, cool. So, going to switch this over to start talking about our repeated measures ANOVA. Okay.
Quick question.
Oh, yep, sorry.
The equivalent of the t-test for categorical variables.
What's that now?
The equivalent of the t-test, but for categorical variables.
Yes.
Which one would be?
Well, it depends on whether or not we're talking about between or with.
Dummy variables. Is there a t-test for dummy variables?
For dummy variables? In what context? Like, so
You have 2 dummy variables?
So I've got a yes-no measured at time 1 and a yes-no measured at time 2. I'd have to look into that. I'm not sure off the top of my head. Yeah, email me and I'll go through and take a look at that. All right. So when we take over and sort of start thinking about our repeated measures ANOVA model, right? So taking from our paired sample test and start thinking about having more than 2 assessment points within a set, okay? If we're thinking about our between subject design, right? We're assuming that our individual cells are going to be independent of one another and uncorrelated with one another. So I've got treatment 1, treatment 2, and treatment 3, right? My assumption is that sort of the first person in treatment 1, their score is uncorrelated with the first person in treatment 2, and their score is uncorrelated with the first person in treatment 3, because we've got different people sort of representing all these different cells, okay? So we're expecting no association with our between subjects designs across our individual measures, okay? So if we're thinking about this as condition 1, condition 2, condition 3, this is sort of one person, this is a different person, right? We're assuming that none of these scores are going to be correlated with one another, okay? But let's say that instead, what we do instead of running this as a between subjects design, where we have, say, 20 people in treatment 1, 20 people in treatment 2, 20 people in treatment 3. Instead, what we're going to do is we're going to have the same person or the same group of people complete condition 1, condition 2, and condition 3, okay? In this case, I'm going to use the same participant, so these aren't different people. This is all the scores from the same person on 1, 2, 3 separate occasions, okay? In this situation, our expected correlations between our treatments is almost certainly not 0, right? Because Tamara is my person 1, and probably what she scores in the first condition probably going to be in some level related to her score in the second condition and the score in the third condition, right? And Chris is going to be my participant 2. His score here is probably going to be correlated to some extent with his score here. Same thing here. Same thing, Siles, here, here, here. Now instead of having a sample of, if we have, in our twin group design, we have 20, 20, 20, so we have 60 people. Now we just have one sample of 20 people going from treatment 1, treatment 2, treatment 3, okay? What's going to happen is there's going to start to be correlations between these individual treatments, right? In general, when we've got correlation between treatments, it's going to be problematic, right? It's a violation of our basic assumptions of our independent samples test. We're assuming that everybody's samples scores are uncorrelated because they're different people in different conditions and things along those lines. When we start having people complete multiple conditions, all of a sudden we create a dependence among our scores, which normally would be problematic, right? So if I've got I'm running a between groups test, right? Or repeat different ANOVAs. So we've got one group of you doing this thing, one group of you doing this thing, one group of you doing this thing. I want to compare those groups, right? If Alicia's looking at Sean's stuff and so they're sharing answers and they're in different groups, and Nick and Ignacio are sharing it, like that, it creates dependency, and that's problematic, right? But if our repeated measures design, we know and are explicitly introducing a correlation between our conditions, right? But because we know what's going on and why that's happening, we can go through and model that association. And what we can do is we can, when we account for it, it starts to reduce error and individual differences within this design. And if we can account for it and we can pull it out of that error term, it starts to make for very, very powerful designs. So, if we're looking at this, right, what we're seeing in this table here is we're seeing a lot of variability within treatments with only very slight differences between treatments. Chris, why is looking at this table, how am I concluding this?
Because since they're the same subjects, they're going to have some interdependence with their scores, right?
Okay. But if I'm looking at sort of this table here, when I say there's a lot of variability within treatments and only a little bit of differences across treatments.
Oh, like where are you pulling that from?
Where am I pulling that
So the between treatments is at the bottom.
Yep.
So those 3, and then the within treatments is in each treatment.
Exactly. So if I'm looking at this, within A, huge differences across scores. Within B, huge differences across scores. Within C, huge differences across scores, right? Ignacio, what is the differences of my condition means here?
They are very small.
Very small, right? And so if I was running this, Nick, with a between groups, a standard ANOVA model, would I likely find a statistically significant effect here? No. I've got massive within group differences and only very, very slight between group differences. This is not going to be, this is going to come up null every time, okay? But if I'm going through and if I'm looking at this closely, a lot of the individual differences that I'm seeing across here, if I'm thinking about this in terms of within subjects, a lot of the differences that I'm seeing within groups is a function of differences within people, has nothing to do with my treatment effect. So if I go through and I say, okay, this isn't, they're all different individuals. We go through and we say, okay, this is actually, to run this as a within subject design, all of a sudden things change quite a bit, right? Because I see for participant 1, this is Chris C, starts at 2, then goes to 4, and then goes to 7, right? Person 2 is Alicia. She starts at a very different place, 10, then she increases. Next to the third person, starts at very different, increases. Even though everybody's starting in very different spots, everybody's changing in kind of the same way, right? And so what we see is a treatment effect that's consistent and reliable across all individuals, even though people are starting out in very, very different places, okay? So if we're thinking about how we go through and start to partition this, what we've seen in this situation is a lot of individual differences, right? But if I'm going through and I'm keeping the same people and looking at their scores over time or across repeated assessments, we're seeing that even though we've got wide variability across individuals, a lot of individual differences, everybody's changing in kind of the same way in terms of the means across these repeated assessments, okay? And so with the repeated measures design, what we have you have our repeated measures means here, right? But then we also have our subject means. And our subject means are again showing a lot of differences there. But what we're going to do is we're going to start to pull that out, right? These differences across subject, these translate into the correlation of our measures. And what we do is we can start to model that. Okay? So with our repeated measures design, what we're doing is, in this case, right, all of this within subject variability, where's this going? Where is it tomorrow? This is all there, right? Making that denominator of our F massive, right? But in the repeated measures case, what we've done is we're going to partial out that individual difference, right? We're going to partial out those individual differences that's producing that interdependence across these scores. What we do is we then taking that individual difference, if we take it and say, all right, this is differences, or this is variability due to individual differences, sort of individual person characteristics, and take that out. If we take that out of the error term and put it somewhere else, now our error term becomes much smaller, right? And what we get is a much, much more powerful test. We get less noise because everybody's existing as their own controls, right? So the difference between where Alicia starts and where Nick starts, and where Chris starts and where Sean starts, doesn't matter anymore, because we've said, oh, that's just a difference in where they start due to sort of individual differences. We're going to section that off, and all we're going to be then focused on is the pattern of differences across once we've accounted for that and taken it somewhere else. Okay? So the correlation between measures starts to become very, very important. As the correlation between measures starts to increase, the power of our test also starts to increase, because we're taking all that individual differences and sectioning it off. Okay? You can kind of see conceptually the difference between what's going on if we look at this as a within subjects effect, within subjects test as opposed to between subjects. Okay. So, with our one-way repeated measures ANOVA model, what we've got is we've got one group of people, right? And we're just taking that one group of people, that's our sample, and we're just measuring these measuring these individuals across multiple occasions. Okay. And so our question with our one-way repeated measures ANOVA, we're just asking, do scores vary across repeated assessment of some outcome? Okay? And our null hypothesis here is going to be that repeated measure, the mean of repeated measure 1 is equal to the mean of repeated measure 2 is equal to the mean of repeated measure 3. Okay? Our null hypothesis, our repeated measure ANOVA is just saying, do our mean values stay consistent across repeated measures? So if we think about this, and so to reference our table up here, what we're going to do is we're going to take it through and take our sum of squares total, right? Just like we took with our original thing. We got our sum of squares total. Our sum of squares total is just going to be the sum of squared deviations of individual scores from the grand mean. Okay, this is all the variability in our set. This is all the total piece of the pie we're sort of working with. And what we're going to do with our repeated measures, always think about our repeated measures designs as first taking that total and partitioning it into within subject variability and between subject variability. My between subject variability here is going to be the mean of my participant means, right? So here's participant 1. This is Alicia, right? If we take Alicia's mean across all three of her, the repeated assessments, that's her mean score. Take Nick's mean across the repeated measures, that's his average score. Chris, Sean, right? What we're going to do is we're going to take the sum of the squared deviations of individual means across repeated measures, subtract that from the grand mean. We're going to take the sum of those squared deviations, multiply it by the number of repeated measures, and that's going to be our sum of squares between. That's going to be what we conceptualize as the variability, the portion of the total that's just due to individual differences, right? Now, if everybody was the same, right? If everybody started in the same place and everybody changed the same, there would be no individual differences. If you're all clones and you all respond exactly the same way, then this is nothing, right? And then, so we're not so worried about that. That's not how the real world works, right? Particularly in psychology stuff, massive differences across individuals, right? In terms of their response style, how they, what they come in with it that day, huge individual differences. In our repeated measures design, we're just taking that out, we're taking it over the side. Then what we've got is we're left with our within subjects differences, right? That's our within variability of our within subjects is going to be due to the variability due to our repeated measure, plus other just general error stuff going on. Okay, so sum of squares for our repeated measure is going to be the mean of our repeated measure, right? Sum of squared deviations of our repeated measure mean from our grand mean times the number of people in our sample, right? It's going to be 4. And then our sum of squares error here, we're going to get this by subtraction. This is going to be our total minus our between minus our repeated measure is going to give us our error here. Okay. So what we've done, so as we're thinking about our repeated measures design, always thinking about is partitioning our total into between and within. Okay, between all of the things that would normally go into our error term that are attributable to individual difference, we're taking that out and we're sucking that out and we're putting that and modeling that specifically as individual difference error or as individual difference variability and setting that aside, right? And what this is doing is it's absorbing the correlation between our repeated measures. So why these things are associated, we're taking it apart and then we're just left with the pure sort of measure of change across our means. Okay. And this ends up making for a very, very powerful test. You'll kind of see how this is sort of partitioning things out and sort of moving things around. Questions about this? Okay. So some assumptions of our repeated measures design. We talked about this as a limitation of our repeated measures because it starts to, there's more things that we have to start thinking about. Not too much with just a one-way repeated measures, I know, but some things we need to think about. So we are assuming normality in the distribution of sample means. CJ, you made eye contact with me.
We should have looked down next time.
You don't look me in the eye. You don't ever look me in the eye.
We should know this by now.
Right. So when we say we're assuming normality in the distribution of sample means, what are we talking about?
It's the normal curve, same as the population.
Okay. Are we, so for our assumptions of our means-based test, are we concerned with the actual observed data so much? No, right? The assumption deals with the distribution of sample means, right? So I could have so my observed scores could be really nasty, okay? What are the two conditions under which the distribution of sample means starts to become normal very quickly? Yeah.
Increased sample size.
Increased sample size.
And I don't know if that other one is.
Someone have it out? Population is normal, right? So if I have if I'm pulling from some measure that has a normal distribution in the population, even if my observed scores are kind of nasty, let's say I have a sample of 50, right? Even if my observed sample is kind of gross, right? But I know that whatever I'm measuring, let's say it's sort of IQ or something like that, height, that has a weight, so that has a normal distribution. I know that even if my observed scores are nasty, the sampling distribution of that, if I sort of take the sample, resample over an infinite number of replications and calculate the mean, distribution of sample mean is going to be normal, right? But let's say I'm not. Let's say I'm Nick and I'm measuring binge episodes in a month in undergraduates drinking alcohol. That's not a normal. That's not a variable that has a normal distribution in the population, right? But if Nick is collecting samples of 50, you know that at that level, even for a metric or a measure that has a skewed distribution or non-normal distribution in the population, as long as your samples are fairly large, sampling distribution starts to approach normal very quickly with reasonable size samples, right? So same thing with ANOVA t-test, things along those lines. I'm less concerned with the observed distribution that I'm looking at, although we need to sort of take a look at that. What I'm more concerned with is the distribution of sample means, right? And so if I've got violations in in normality in my observed variables, our test is pretty robust to that because that's not what we're necessarily concerned about. But if I'm seeing non-normal data, I start to get increasingly concerned when I have, again, a combination of things. So I've got a different shape and unequal variance, right? So not only are my observed scores not normal, they're skewed and sort of massive differences across. So time one, my standard deviation let's say is 10, and my standard deviation at the second time is 100, and I've got massively skewed distributions. then I'm starting to worry about that, right? If I have unequal variances and unequal sample sizes, then I'm concerned about that. I've got violations of normality in small samples, right? My data are nasty, and I've got cell sizes of 10. That's no good, right? If I've got distribution of scores at time 1 are wildly positive skew, and at time 2 they're wildly negative skew, then that's problematic, right? So we're concerned about doubling down on violations. Okay? So we're assuming a homogeneity, or sort of normality in the distribution of sample means. We're also assuming in our repeated measures ANOVA, with our one-way ANOVA, homogeneity of variance across individuals, or excuse me, across intervals. So I'm assuming that the variance at time 1 is roughly equivalent to the variance at time 2, is roughly equivalent to the variance at time 3. Okay? So I'm assuming that whatever I'm measuring, variability in my scores is equal across repeated assessments. Now in our between subjects group, right, so with our like one-way ANOVA, we're assuming homogeneity of variance across groups. With our repeated measures, we're assuming a homogeneity of variance across assessment points. Okay. What we typically do to test this, calculate an Fmax statistic. Did we talk about Fmax last semester? I don't think so. Fmax is just a ratio of your largest variance to your smallest variance. Okay. So if I go through and I have, say, 4 repeated assessments, what I would do to calculate my Fmax is I would look at, take the variance of my largest variance across those 4 measures, divided by the smallest variance across those 4 measures. That's going to give me my Fmax ratio. Okay. For these repeated, we can have pretty large differences in our variances and still be okay. Now, can I have different sample sizes if in a one-way repeated measures ANOVA? No, yeah, you're absolutely right. Why not tomorrow?
Because then that, if you were missing data for like one of the matched people.
Yeah, there you go, right? It's just basically I just got the same group of people. These are all the people. I just need to have them. I'm just measuring them on multiple occasions. If someone is missing a score, then they get kicked out. And we can't, with this traditional stuff, we can't deal with that, right? So we can't have different sample sizes because there's only one sample. That's all the people that we have, right? And in this case, you'll say Fmax up to less than, the tests are robust Fmax to less than 10. Which if you think about it, that's a massive, so that's saying the ratio of your largest variance across repeated assessments differs from your lowest by a factor of 10. That's pretty big, right? In psychology, because again, we have limits to sort of what the highest and lowest value is for our scores can be. We often don't hit that, but in some other areas, right, if I'm looking at some sort of continuous outcome where the upper limit is infinity, we might start to get huge differences there that start to make a difference. But again, the assumption is that variance across our repeated assessments is sort of ballparkish. Okay. So Fmax is just kind of a value. There's not a significance test for it. We're just kind of eyeballing it and seeing what's going on there. All right. Other assumption that we have, it's a little bit different with our repeated measures designs. We have assumptions about the variance covariance. Okay, so for our repeated measure ANOVA design, what we need to do is take a look at our variance covariance matrix. So this is sigma hat across our repeated measures. So if we're going down through and looking at here, we've got assessment 1, assessment 2, assessment 3, assessment 1, assessment 2, assessment 3. Right? And what we're going to do is we're going to calculate a variance covariance matrix. So these on the diagonal, we've got our variance estimates, right? Which is basically a measure of what, Siley?
Variance estimates?
Covariance, yeah.
Variance estimates are the variance of the difference, or something about the difference?
Okay, kind of, yeah, you're on the right track. What it would, so in layman's terms, what is covariance a measure of? Someone help her out? Yeah.
not that your outcome Y varies in accordance with a change in X.
Yeah, the thing about covariance is basically a different metric of your correlation, right? So what we've got in our diagonal here is the extent to which, this is variance estimates. This is the variance of variability at measure, variance at measure A, variance at measure B, variance at measure C. Okay, your off diagonal, that's your covariances. Off diagonal is the extent to which measure at time A measures with covariates with time B, A covariates with time C, right? So these are kind of like correlations or associations here. Okay. So when this variance covariance matrix has the property of compound symmetry, we would say that the variances of our repeated measure are equal and all the covariances are equal in the population. Okay? So compound symmetry, and you hear this, refers to if this variance covariance matrix, again, I've measured someone on a group of people on 3 different assessment points. This is the variability 1, 2, and 3. This is the extent to which those various measures relate to one another. If this matrix exhibits the property of compound symmetry, we're saying that in the population, the variance at time 1, time 2, and time 3 are all equal to one another. And then also all my covariances are equal to one another. So time 1 relates to time 2, and time 1 relates to time 3, and time 2 relates to time 3, all the same way. So basically think about this. Variance is all the same across each one of our repeated measures, and all of our, the correlation between all of our measurements is equal to one another, okay? So we're saying if we're talking about, instead of covariance, think about correlations. This is 0.4, this is 0.4, and this is 0.4. They're all equal, right? Each one of my repeated assessments relates to all the other repeated assessments, all in the same fashion. Variance is equal across each one of these things. If that were the case, we would say that this variance covariance matrix exhibits compound symmetry. Now, compound symmetry is overly restrictive. It's not necessary for our assumption of our repeated measures ANOVA. But what is an assumption of sphericity. Okay? Sphericity, we would say that this variance covariance matrix exhibits sphericity when each pair of our repeated measures, or the difference score of each pair of our repeated measures, has equal population variance. Okay? So this is saying if I took scores at time 1 and scores at time 2 and created a different score, I took scores at time 2 and time 3 and looked at those different scores, and difference at time 1 and time 3 and looked at those different scores, if all of those different scores had the same variance, then we would say that matrix demonstrates property of sphericity, and that's an assumption of our repeated measures of ANOVA, okay? Or our repeated measures of ANOVA. When this doesn't happen, though, what happens is we have our F ratios that we're calculating aren't distributed as the expected F ratios that we would expect, and what that does is it creates bias in our sample. And this is kind of a tough thing to wrap your head around, sort of mathematically. Like, okay, essentially what it's saying is that if I calculated the difference between time 1 and time 2, difference in time 1 and time 3, difference in time 2 and time 3, and looked at the variances of each one of those different scores, they would be equivalent to one another. But, and so if we've got criteria for sphericity, but I can have something that doesn't meet compound symmetry but still meets sphericity. So sphericity is a less restrictive assumption. Now conceptually, what's going on? Mathematically, sphericity is our assumption of our, technically this is the same thing with our between groups design, right? If we have just a straight up one-way ANOVA between groups, I have group 1, group 2, group 3, we still have a sphericity assumption, right? But because we've got different people in each one of those conditions, what do we assume the correlations between any individual people's scores are? 0.
Oh, wouldn't it if you're matching the same people?
No, different people.
Okay.
So a straight up between groups design, right? So U3 in condition 1, U3 in condition 2, U3 in condition 3. I expect no correlation between Alicia happens to be the first person in subject in condition 1, Sean is the first person in condition 2, Tamara's the first person in condition 3. You're all different people. I assume no correlation between your measures, right? And so our between group design still has an assumption of sphericity, we just assume that the off diagonal is all 0 with that. We don't have to worry about it, right? With repeated measures at ANOVA, we assume that our covariances aren't 0, right? So now we have to start thinking about this. And so when we start thinking about applied applications of our repeated measures designs, we know that sphericity is an assumption. We're just assuming that we would never achieve this, okay? And when we're thinking about what that means, right? Let's say we're doing some developmental work. Tomorrow we're doing some developmental work, right? So we're going through and measuring people at age 12, 13, 14, and 15, right? Okay. What we assume, with whatever we're measuring people on, I'm going to assume that in general, my measurement at 12 and 13 are going to be more similar than 12 and 14, and 12 and 15, and 12 and 17, right? And 16 and 17 are going to be closer together than 16 and 14 or 16 and 12, right? And so as my measurements get farther and farther apart, I'm going to assume that they're going to be more different than one another, than stuff that's right up against one another, right? And so what we see is a basic violation of sphericity here, right? The sphericity says that the variance between any two combinations of my time point is all going to be equal across all assessments, but it's not going to be, right? This is going to be these two measures are going to be much more different than these two or these two, right? And so this is a developmental sample, we're talking about years and years, but even if I'm going through, and you've got people coming in, like you're measuring impact of sort of alcohol or alcohol expectancies or something like that, and you're having people sort of drink something that may or may not have alcohol in it, right? You're going through measuring sort of euphoria or something like that, and you're measuring, so you say, okay, you're going to have to start drinking and measure 10 minutes at 10-minute intervals across, say, a 40-minute sort of trial drinking, right? I'm expecting my measure of sort of feeling the effects, how drunk or buzzed I am at time 1 and 2 to be very much more similar than time 1 and time 4, and time 3 and time 4 to be similar than sort of these other two, right? And so because adjacent assessments are probably going to be more similar than assessments that are quite far apart, what we know is this is going to produce a violation of that sphericity. Because if sphericity holds, then the difference, variability between these two is the same as variability between these two, variability between these two, variability between these two, all possible combinations. Just the nature of this design and sort of maturation is going to make sure that that's rarely, if ever, the case. Okay? Do people see kind of from a conceptual standpoint why we're assuming that within these repeated measures designs that sphericity never holds? Kind of getting some idea about this. Okay. So what's nice, if we have a assumption that never holds, is then we don't have to worry about screening for it a whole lot, because we'll just say, well, it's not going to hold. We'll just assume that this doesn't hold. Well, what we then need to do is provide some sort of correction for it. So we've got a couple different options, and these are just things that are provided in the SPSS. Moxley's W is a statistical test of deviation from sphericity, but underpowered, right? So if it's underpowered, it's going to say there's no violation when there probably should say that there's violations. If our data aren't normal, that gets screwed up. And so generally what we're going to do is just ignore that as a test and not even worry about it, right? So what we have is we have corrections for violations of sphericity, okay? And what this generally involves is some adjustment in our degrees of freedom depending on the extent of the violation. And the extent of violation, depending on what statistic we're calculating, is sort of given an estimate using this epsilon, okay? So if I have epsilon equals 1, it says sphericity assumption is met, right? The variability or the variance of all my sort of different scores across all my repeated measures are all equal. That would give me epsilon equal 1. I don't have to worry about it. But because we know that this is not the case, we always assume some violation. But as epsilon decreases, our violations of sphericity become increasingly severe, and our correction becomes sort of greater and greater with this. Okay. So two options that we have, and so we'll think about in terms of SPSS output. We've got a greenhouse gas correction. What we're seeing is a downward adjustment of our degrees of freedom based on a greenhouse geyser variation of epsilon hat here, right? And Chris, so if we think about the greenhouse geyser correction as my violation of sphericity increases, we're seeing a downward adjustment in degrees of freedom. What does that do to the power of my statistical test? If my degrees of freedom go down? Is it easier to claim, is it easier to find statistical significance?
An adjustment to decrease the test.
Yeah, right. So think about, remember, if I've got a t-test with 20 degrees of freedom versus a t-test with 100 degrees of freedom, okay? My critical value for that test is going to be smaller for the 100 degrees of freedom or the 20 degrees of freedom. Which one is it going to be smaller? Which one is it easier? 100 degrees of freedom, right? Because we're assuming a more precise test, so less deviation, right? So what we're doing with these with the greenhouse geyser, what you see is a decrease in the degrees of freedom. So my test might have 50 degrees of freedom. With my greenhouse geyser correction, you see that it now has 30 degrees of freedom, right? That sets the marker for me to claim statistical significance as more severe, as I have to get a bigger score to claim statistical significance than less. Okay, where did we see last semester a similar sort of adjustment on our degrees of freedom? What's that? Oh, yeah, 2P, but that was a different thing because that's sort of an adjustment for multiple comparisons. What about our t-tests? What's that?
Stuff?
Yeah, right. So when we're looking at our between our independent sample t-test, if we had a violation of normality, what we would see is a corrected t and a corrected degree of freedom. Your corrected degree of freedom is never larger than what it is in sort of the straight test, right? It's always a decrease in your degree of freedom, and so then that increases sort of the critical value that you would need to achieve, right? And so this is what's going on with greenhouse geyser correction. Is we see a downward adjustment for our degrees of freedom based on the greenhouse geyser variation of epsilon. Hunfeld is another correction, alternate estimate of epsilon. And so we would say that you would use, traditionally say you would use this when the estimated value of epsilon is greater than or equal to 0.75. It's a less severe correction than greenhouse geyser, but don't just use greenhouse geyser. If you're on that margin, right, your findings are questionable enough, right? Yeah.
How does it adjust the degrees of freedom? Like in what way does it adjust?
It makes the degrees of freedom smaller.
It's just like guesses. It's just like you have 20 people on and you have 15 people.
No, it's there's formula and stuff like that. You don't really need to worry about that, right? That's sort of more. That's some nerd stuff we won't make use of go through on that. Yeah.
So you put this into SPSS and then you say run this and then figure it out?
SPSS will do it automatically, so you don't need to worry about it. It'll
Okay.
give you these statistics. We'll talk about that, right?
So it also will check then for
Yep.
the sphericity?
Do we need it to? It will check the sphericity. It'll give us Moxley's W, but do we care about that?
Well, because it says becoming increasingly severe, it decreases the epsilon, so I'm just
Right.
curious, like.
We don't ever worry about it. So when I said, do we ever worry about Moxley's, you shook your head and said no with a look of disgust. Why?
Because it's unlikely that we're ever going to meet that assumption.
Yeah, right. So we're always just going to assume that we have a violated assumption and just move straight to greenhouse geyser correction. Another reason not to use Hunfeld is Howell notes that Hunfeld correction in SPSS and SAS isn't right. It's wrong, right? I checked the new version, it's still wrong. It's been wrong for years and years and years, right? And so we're not going to worry about this. We'll just use greenhouse geyser correction. You all should be happy about this. This is one last thing, the decision point that you have to make in terms of moving forward with things. So this is at one point in time a sort of a hot topic on how we adjust for corrections of violations of sphericity. Don't have to worry about it now. Just use a greenhouse geyser correction, report that. Okay. All right, that does it. What we'll do is, okay, and then just summary of our repeated measure designs. So what we'll start off with next Wednesday is we'll jump into actual sort of data stuff. So we're way ahead of the game, which is good. It gives us a little more time to go through and spend on examples. What we'll do for these repeated measure stuff, and you guys can start packing up. So Sean, you can turn that off.